clicker. Good. And so flip the slides in the laser. Okay. So our first talk in the afternoon will be our hangover from the morning, Mei Feng. Mei Feng was a grad student at Columbia, and then she was my postdoc for a while before moving to BU, Argonne, and then Brookhaven in quite a rapid succession. So, and we'll hear about attempts to do multi-grid in HMC.
Okay, so let me.
Can you tuck the thing in your belt? I think it won't pick up as much. It's when you hold it in your hand. For some reason.
Okay, let me see.
Your hand is going to.
Okay, that works. Yeah, so this work is done with Rich and James, and this is still work in progress. So I'm just going to give you a progress report. And so just a brief history or timeline. The project started in the winter of 2012 at BU when Rich said he had some leftover grant from NSF and I wanted to, start thinking about working on multi-grid for the HMC. And 5 months later, I moved to Argonne. So, and I continued working on this project with James. And 6 months later, I got my current job at Brookhaven. So since then, the progress looks like this. This is actually an actual evolution plot for the topological charge in one of our gauge ensembles. So it's completely frozen. So this is also a difficult algorithm issue, but this is not what I'm going to talk about today. So the results are very preliminary, but they already look quite promising. So I hope you agree with me after my talk. So the outline of my talk is the following. I'll first give a brief review of the HMC algorithm for lattice QCD. Berlin already talked quite a bit about it. And why we want to use multi-grid and HMC, and what are the difficulties associated with it. And then I'll show you our implementation strategy and some preliminary results with an improved Wilson fermion. So we still haven't implemented the cover HMC in the framework that we're using right now. And then I'll show you some possible improvements for the future. So the HMC algorithm, first we introduce the conjugate momenta of the gauge field, and we construct a Hamiltonian like this. And we update the gauge links and conjugate momenta with the Hamiltonian equations of motion. So you can integrate these two equations by finite steps. And here, the action is actually expressed in this way. So you have the pseudo-fermion action because we don't really know how to deal with Grassmann variables, and then the gauge part. And the pseudo-fermion action looks like this. So D is the Dirac operator. This is for the one flavor system. And in order to update the conjugate momenta, you need to calculate the force term. And this term here includes both the contributions from the gauge part and the fermion part. And then after the update for one trajectory with n steps, then you'll decide whether to accept or reject the current new configuration of the gauge links through the metropolis step. So the workflow in HMC goes like this. First, we'll use a heat path to choose the conjugate momenta according to this distribution. And we actually, and then we need to generate some Gaussian noise. So you use heat path again to generate this, and then set the pseudo-fermion field to be d Dagger eta. So you'll get the pseudo-fermion action, like as shown here. So this way, you actually get a two-flavor system. So you get phi d Dagger d inverse phi star. And then you update the momentum, the gauge links according to the previous equations of motion for n steps, and then you have a trajectory length. Tau is usually set to 1. So you have a unit length trajectory. And you decide to accept the new gauge configuration if the change of the Hamiltonian is negative. So this one will be larger than 1. Otherwise, you accept the new gauge configuration with the probability of this. So what you really want to do is to keep the change in Hamiltonian small so that you will have a high probability of accepting the new gauge configuration. Otherwise, you get stuck in the phase space. So I'm not going to talk about the integrators, but the trick to keep delta H small is to keep the forces small or use small step sizes, because the discretization error will be determined by the step sizes and also the force term. So what I care about is the matrix inversions in HMC. So there are several places where you'll need the matrix inversions. First, when you assign the pseudo-fermion field at the beginning, if you use just a regular pseudo-fermion action without the Hasen-Busch style terms, then you don't really need to do the inversion, because you can just set phi equal to the product of the matrix D and the noise. But if you use the Hasen-Busch terms, then you'll have additional terms like this. And in order to get this action, after you generate a gauge noise, you generate a random Gaussian distributed noise, then you need to reconstruct the pseudo-fermion field using this set of equations. So here now you see when I is larger than 1, then in addition to this is the regular term. In addition to this term, you'll have some terms involving the matrix inversions. So with n Hasen-Busch mass terms, the setup will require n matrix inversions. But this is still not the big cost of HMC, because with the Hasen-Busch mass terms, usually the masses are heavy, so these inversions are not that hard. And then we need to calculate the initial and final Hamiltonian, because then we can use it to decide whether to accept or reject the new configuration. And here it will also involve some matrix inversions. But again, you only need to do this twice per trajectory, so it's not a big cost. The most expensive part of the HMC comes from the fermionic force term calculation. So this, you want to see how much the action changes when you change the gauge links. And so you can evaluate the change in action. So if you write it out in terms of the matrices and the pseudo-fermion fields, you'll find something like this. So this doesn't have the Hasen-Busch term, so this is just the regular pseudo-fermion action. And Q here is MM Dagger, or M Dagger, depending on which convention you use. And you see here, you'll need the inversions. And basically, you need this matrix inversions at every integration step. And when you use the Hasen-Busch mass terms, so now I just being sloppy, I dropped the hats on the matrices. here. So I use M hat to indicate that this is actually even or preconditioned Dirac matrix. Yeah, so here, when you have the one Hasselbusch term, I denote it as W, then you will need to calculate the y vectors, which is written in this form. So you need to do, again, the Q inverse. And one thing I like to note is that for Wilson fermions, you can actually rewrite the change of the gauge action in this form. So you have the original matrix, and then if the Hasselbusch mass is given by kappa delta, then you can rewrite the change in action in this form. So you can see when kappa and kappa delta are close together, this term is actually very small, so it'll go to 0 if you set them to be the same. And this basically means with the proper choice of the Hasselbusch mass term, you'll be able to reduce the size of the force term, which allows you to use larger step sizes. And this is why Hasselbusch trick works pretty well for HMC. So overall, from the previous few slides, we can see that the core of the calculations in HMC is solving this equation. So why do we want to use multigrid? HMC in lattice QCD suffers from critical slowing down in several aspects. The first one is basically the same for HMC or just the quark propagator calculations. The condition number of this operator becomes worse as we decrease the quark masses. And the computational cost of the inversions for the force term here will increase dramatically. And another problem is that the contribution to the fermion force becomes larger as the quark mass is decreased. So this is assuming we use the same algorithms but change the quark masses. So when you have a larger fermion force, then you need to use smaller step sizes, which means you need more integration steps and more matrix inversions. And so this is why when you go to a light quark region, your HMC, the cost to generate the gauge configurations increases a lot. Third point is the autocorrelation time may become longer when you have a lighter quark mass, and you'll need more trajectories in an ensemble to get the same number of independent gauge configurations. So that means you need a longer ensemble and a lot more inversions. So you can see there's a lot of room for improvement in the HMC algorithm because there's so many matrix inversions involved, especially when you go to lighter quark masses, larger lattice volumes. And this is essential if you want to go to the physical limit eventually. So now we have a lot of collaborations generating ensembles at the physical quark masses. Yes. But we also want to go to the continuum limit, so you need finer lattice spacings, which means more lattice sites if you want to keep the volume fixed. And if you want to do finite volume effect studies, you need to generate a lot of different lattice volumes. So if we can speed up the HMC algorithm, we can really benefit a lot when we try to go to the physical limit. And as you've seen so far in many talks, a multigrid has proven to be very efficient, at least in the quark propagated calculation. So you can achieve 10 times or more speed up compared to the normal Quadrant solvers such as CG or by CG stack. So it is natural to think that we may be able to apply multigrid in the HMC. So here's just a reminder of what the performance of multigrid looks like. On the left side is the comparison of the multigrid solver, the black dots, and the CG solver, the green, for one of the anisotropic Wilson lattices at different quark masses. So you can see the speed up is about order of the factor of 10. However, what I want to point out here is that this is the setup cost for the multigrid solver, and you can see that the setup cost is actually several times of the actual multigrid solve time. And again, on the right-hand side, this is the speed up as a function of the multigrid setup time, and the setup time is expressed in terms of the by CG step solves. And you can see, in order to achieve this kind of speed up, the setup time will be several times of the by CG step solves. And we can overcome this in the quark propagator calculations by doing a lot of inversions on the same gauge configurations. For example, if you want to do disconnected diagram calculations, you can use multiple sources, or if you just do a connected diagram calculations, you can also do the inversions for multiple sources. So this way, the overhead of the multigrid setup won't kill your performance too much. But for the HMC, the situation is a bit different. So for HMC, the gauge fields are updated at every integration step. So if we use the same recipe as we used in the quark propagator calculations, then we'll spend way too much time doing the setup. So it defeats the purpose of multigrids if you want to redo a setup every time the gauge field is changed. And the solution is to either reduce the setup cost dramatically or find a way to reuse the setup from the old gauge configuration. And a second problem is probably not really a problem. It's a kind of a happy problem, because nowadays with the Hazen-Busch mass preconditioning and multi-scale integrators, the HMC algorithm has improved a lot since 1 or 2 decades ago. So if we want to really make a case for multigrid HMC, it has to be able to compete with the modern well-tuned HMC algorithms. And that means we need to be able to do efficient light quark solves without much setup cost for a lot of integration, subsequent integration steps. And because in the Hazen-Busch mass preconditioning, a lot of the heavy quark terms are introduced, we should try to speed up the heavy quark solves as well. And if we can use the multigrid solver on top of the Hazen-Busch preconditioned HMC algorithm, then it may help us gain additional factors. So what we did was to make use of the fact that the gauge field, even though it gets updated after every solve in HMC, but it should be highly correlated. Even the gauge fields between different trajectories may be correlated. So we're hoping that the same setup may be able to be reused for several integration steps and even several trajectories if the multigrid parameters are tuned well. And so what we did is to do the multigrid setup at the light dynamical quark mass. So I'm only considering 2 flavor HMC here. So you have the light quark mass in the dynamical simulation. So our setup is done at the light dynamical quark mass at the beginning of a trajectory. And then we try to see if we can reuse the same setup in subsequent integration steps. or the trajectories until we lose the gain from multigrid. And we only refresh the setup when the subsequent trajectory time using the same setup from the beginning is larger than the setup time plus the first trajectory's time or first few integration steps. So we use the multi-grid solver available in QOP, QDP, but the integration into HMC is done in Fuel. Probably not all of you know about Fuel, so I'll show a slide on Fuel. And the multi-grid solver is only implemented for this equation, so the Dirac equation. And in order to do this, to solve this equation, we actually do a two-step solve. First, we solve M Dagger inverse, and then we solve the M inverse with the solution from the M Dagger inverse as a source vector. So Fuel. Fuel is a relatively new library. It's basically a Lua wrapper over the SciDAC3 libraries. So far, it's only been implemented for QOP, QDP. And Lua is a very lightweight script language, and it's very portable. And the advantage of using Fuel is that because it's written in the scripting language, you don't need to rewrite or recompile your program every time you want to use a new algorithm. So we can just easily change the script to use different integrators and different gauge actions or fermion actions. So it's very flexible. And right now it supports most common gauge actions, and it supports full Steiger and Wilson fermions. It means it has the solvers and the HMC force terms. And so far it only supports the Clover solver. There's no force term yet. That's why we haven't done the MGHMC for the Clover fermions yet. And actually the big advantage of Fuel is that it is written such that it supports arbitrary number of colors and arbitrary numbers of fermions. It was started out as a package for beyond standard model simulations, but right now I think it can be quite useful for QCD simulations as well. And so NC can be set at compile time or runtime, so this is very useful for people who want to explore different gauge groups. And here is an example program for an HMC evolution in Fuel. So you first declare a lattice, you set the lattice geometry, and then you set a random number seed, and you decide what kind of gauge group you want. So you're just SU3, and you set the gauge field, initial gauge field, and here you just declare a gauge action. So you use plaquette action with the gauge coupling beta equal to 6, and then you get the conjugate momentum, and then this declares the action for the conjugate momentum, and then you decide what kind of integrator you want. So this is MD. It means you don't do accept, reject, and then the integrators you want, and you feed in the gauge action and the gauge field, and etc., etc. And here you have the Markov chain. Yeah, you declare evolver for the Markov chain, and again you get the both the conjugate momentum part of the action and the gauge action. And again, you need to decide which gauge action you want, which gauge field you want to use, and then you run it. So this will give you an HMC evolution with 40 steps. So a lot of people have talked about this. So the multi-degree solver in QOP-QDP is fairly standard. First, you calculate the neo-noun vectors by basically solving using the iterative solver to random vector zeta. And then you go through the fine level pre-smoothing and then restriction and then cost level solve. And then you prolongate back to the fine level and then you do fine level post-smoothing. And we actually use the then we apply GCR as an outer solver to the preconditioned operator. So this is the tests we've done so far. We start from existing thermalized and isotropic two-flavor Wilson lattices. This is a very old lattices, so they have a result paper in 2009. So the gauge configurations were probably generated in 2008. And right now we just do a plug and play. So we simply use the same HMC setup as these authors, and we just replace the original solver with MG, the multi-degree solver. So they use either CG or by CG step, and we want to see if by simply replacing the solver with the multi-degree solver, we can have some gain. And in the original HMC setup, they only use one Hazen-Busch mass term. So the light dynamical quark mass is this value. So this gives you a pion mass at about 420 MeV. It's a relatively heavy pion mass. And the Hazen-Busch term is a much heavier mass here. And this was run on a 32 Bruegel Q nodes with 32 API processes. So it's equivalent to like 10, 24 cores. And the reason why we chose such a heavy mass and these two small volumes is because we wanted to first make sure the code actually works. And it also allows us to run the tests within the constraints of the test machine in Argonne. So we run this on Vesta, which has a 2-hour time limit. And there's also a constraint on total number of core hours you can allocate per request. So this choice will allow us to at least do some initial testing. And because we use anisotropic lattices, there's an isotropy, and there are various parameters which I don't really care about right now. What I want to point out is that the number of light quark solves in these evolutions actually is only 10. So that means you just need 10 light quark solves per trajectory. And you spend most of the steps doing the heavy quark integration. So for the 24 cubed, they use 40 integration steps for the Hazen-Busch term. And for the 32 cubed, they use 60. And even more integration steps for the gauge term. So as you can see, with the Hazen-Busch trick, the light quark solve is no longer the most expensive part. It's still expensive, but it's equally expensive for the heavy quark and the gauge force calculation. And the stopping condition is 10 to the minus 8. So now, before we can really see if multi-degree works in HMC, we need to go through a lot of parameter tuning. So this is a table for some examples of the runs I did. So there are many more that I tried, but this one seemed to be the most promising. So you can see there are a lot of parameters to tune. So you need to set the residual for the multi-degree setup and the residual for the coarse operator setup, and then various things. And we use, from run 1 to 4, we use 24 noun vectors. And for run 5, we use 16. So this is for 24 cubed. And the parameters are quite similar for 32 cubed. And And then here I show the setup time with each set of parameters. And you can see they don't vary a lot. So this one has the least setup time because I use the smallest number of non-vectors. However, when you go to the actual walk clock time for each trajectory, you see quite some variation. So this one, when you, I need to point out that the setup is only done once at the beginning of the first trajectory. So after the setup, you evolve for one trajectory. This is the total time for the first trajectory. And then this is the total time for the second trajectory, and so on. So you can see the time actually varies quite a lot for different choices of the parameters. And then I want to point out that it turns out the best choice is the parameters in run 5. So even though in run 4, you see that the time it takes to finish the first trajectory is the shortest for run 4, it gets much worse very quickly as you go to the next few trajectories. For run 5, even though you lose a little bit of time in the first trajectory compared to run 4, the time doesn't really get much longer when you go to the later trajectories. So this is the best choice I have. So this is quite interesting because even though in run 4 you spend a lot of time in the multi-grid setup, you expect it to speed up the solves much more than with this setup. But the problem is the same setup may not work as well for subsequent gauge fields. So the efficiency of the multi-grid solver decreases very rapidly compared to run 5.
Mei Feng, I have a question. I'm sorry. I'll go first. What was a typical trajectory time if you didn't do multi-grid?
I will show you later. I'll show a
okay.
comparison.
Do you have a question?
What's the trajectory length?
Yeah, so the trajectory length, they have a kind of weird normalization. So the trajectory length is kind of this one, 1 over square root 2.
So in our class it was 1, but
yes. Yeah. So in a typical, yes. In a usual convention, it's 0.707. Yeah.
So how many time steps did you look at how the solver is performing in certain cases in terms of the number of iterations it needs to reach this tolerance set, or
Sorry, I couldn't hear.
how the solver is performing?
Multi-scale.
You mean with the same setup?
Yeah,
Yes.
because using more vectors is not necessarily better, especially the way James did it, right? I mean, once you have some redundancy in these vectors, the solver can get a lot worse. And I don't think he does a QR locally or anything like this. He just takes the vectors, puts them in P, and that's his P. He solves. So,
You can see that the solver actually.
QR, right? Or James also. So, I mean, at least when I remember, it was just taking these vectors and then putting them in P. Right? I like the QR. You know,
Yeah, I thought he did too. I think he gets a vector. I think he gets a global vector, and then when he restarts, he starts on an orthogonal direction from that vector, at least, right?
he just has to.
Yeah, but at the end, but maybe he doesn't do it at the end of the new
I
vector.
mean, more vectors and more setup that would be better solver unless you're very careful.
Well, I mean, but this actually
It is in this case though, because you can see the trajectory. The first trajectory time is the shortest among all these choices.
But this is curious and goes to the question of whether you really want eigenvectors. It seems to me. I mean, in other words,
Sure.
it is curious that you had better resolution presumably on low eigenvectors when you worked harder, but then as the fields evolved, they kind of straggled out, and it did better after that. So it's a very peculiar. Can you understand this? I mean, it's kind of peculiar, isn't it?
There could be local redundancy that could really ruin the result. That's what I'm trying to say. You have local redundancy in your peak.
You think that might be
these
a?
aggregates, you're going to get back condition much worse than if you make sure there's no redundancy. And that's why not only do you do a QR, but oftentimes you can do an SVD to trim these spaces or the number of vectors.
But okay.
You'll get much better performance.
Okay, but let's suppose all that was just perfect. Then isn't it surprising that now you've moved to a different matrix, you've evolved the field, right? And using a less good solve for the first one, which you actually designed it for, is better for the evolved field. Isn't that bizarre?
Well, what I'm thinking is that these vectors are not as accurate there, so maybe you don't have this local redundancy problem.
Yeah, but
It depends on.
so you think if that was solved, then you would be very surprised by this. It wasn't local redundancy.
I mean, this is something to check. I mean, it is curious that somehow.
In other words, they're using the preconditioner for another matrix to do the new matrix.
I understand, but
Yeah.
I mean, the number of vectors is a subtle issue, and how you filter and sort these is also subtle. Don't do it right. Adding more vectors or doing more work is not going to give you a better method.
She hasn't changed the number of vectors, do you?
She did. It's 24 on the left, I believe, and 16 on
Yeah,
the
so
right.
these have 24 vectors and
Oh, I
these
see.
have 16.
That's my point. So you probably have enough. You filled your space probably with this 16, and these
Yes.
are 8.
No, but if you look at the first example, you see almost the same behavior for larger number of vectors. So,
Sorry,
and
what do you
the first and the last,
was
scored column. I mean, run 1 and run 5. I mean, the evolution over the trajectories is almost the same. You go up from 160 to something about 200. So there's not much difference, but change the number of vectors. So I don't think that this is really.
It's not just the number of vectors, right? Because you also it also depends on how well you want to solve
This is
the
also,
vectors.
it's also how accurate they're.
Yes.
I think those are the different problems.
So this one has much accurate solves for the noun vectors, and this one's much less accurate. So
I don't know exactly what he's doing, but somehow you have to be careful.
Well, anyway, it would certainly be good to try it with another set of methods. Yeah.
And this is an issue with generating all these vectors simultaneously. I mean, the plots I showed yesterday and also Mike had on the slides today. You're using the method to get the next vector. And then you're somehow sure locally they'll be orthogonal because, you know, the method for the original vector will eliminate anything it can. Right? So it's not clear to me the solver should always get better with the way the setup is done here. That's all. I don't. Yeah. Okay, anyways, I'm just.
Yeah, I think that's right, because that's why, you know, I've tried several different setups just to see which one works best. But for this one, I think if you just consider the solve on the same gauge field as the setup, then this one certainly has the best solve time compared to the others. Because even over...
The original matrix.
Yes. Okay. Even over one full trajectory, which has actually 20 solved, because I solve M Dagger in 2 steps, so it's 20 solved. So you still get the shortest time. So yeah, so I think this setup certainly wins for the first trajectory, but then it doesn't work so well for the subsequent trajectories.
So when you decide to run the setup, right, because maybe your solver isn't good enough anymore,
right?
Do you reuse the vectors you have, or do you start from scratch?
Yeah, so we right now we start from scratch, but that's something that we've been wanting to do. So we use the vectors from previous setup. Yeah, but it hasn't been done yet.
Okay.
Yeah. So when do we decide to refresh the setup? So we decide we need to redo the setup when the trajectory time is longer than the setup plus the first trajectory time. So for example, here, 208 is a bit larger than the sum of this. So we will use the same setup for 3 trajectories. And then at fourth trajectory, we'll need to redo the setup from the gauge location that it starts with. Okay, so
Nathan, when you say trajectory, you mean step?
trajectory. I mean trajectory.
You keep the setup for the whole
Yes,
trajectory?
yes. So yes, I keep the same setup for
Three
three trajectories.
including
Yes.
3 except for trajectory stuff?
Yes, so that's 60 total light solves.
Yeah, okay.
So it actually, I think it needs a bit of luck because if you don't choose the multi-grid parameters carefully, then you may not be able to do this.
In Muscher's case, was he able to keep, when he did the domain decomposition preconditioner, was he able to keep it for a whole trajectory? I didn't think so. It was like 15 steps or something. No, he kept it for some number of steps.
Four steps.
Yeah.
It went away quickly.
But
Wow.
I mean, it's a whole, it's another kind of attitude because you're not starting with a new setup. You're just updating vectors that you have, but just monitoration of your setup if you can speed it up. I mean, if it's an iterative procedure, then you just do like a small update of.
Well, that's what we plan to do here too.
Yeah, sure, you can do this as well.
Yeah.
Sure.
This is just a test. Yeah.
And
I mean, you don't need to do an update for 3 whole trajectories.
I think you should go and explain the whole thing and then get questions because it's.
I don't know. I mean,
No, it's okay.
it might be. I don't know. It might have to do with the heavy prior mass.
Yeah.
Let her go through.
I'm not worried about time.
Yeah, it's okay.
Yeah, I know, but still. I think
I'm almost done, so.
More meaningful when you see the result.
All right. Isn't that result already meaningful?
Yes. Yeah, so there's some other things that I'd like to show. It's quite interesting. So this is actually comparing run 4 and run 5 for the single solve time as a solve sequence. So there are other solves. So there are this light quark solves and the heavy quark solves. So the red ones are the run 4, the green ones are run 5. So you can kind of see at the very beginning the red points outperform the green points, but then it crosses over very quickly. So then the green points outperform the red points. So this is why it's just just another way of seeing this. You see that it gets worse much quicker for run 5, and it stays almost the same for run 5. Run 4.
Is that the number of solves there?
They're here?
No.
It's the solve sequence. So it's just the first solve, second solve. I just basically grab the outputs from the log
Yeah, but
files.
it's not 2,500 solves.
These are over many trajectories.
What?
This plot is over many trajectories. It's not
It's
just
a single setup and it goes for 2,000 solves.
yeah. It's just I just keep it running for many trajectories without redoing the setup. So it's
Where does the original unconditioned time lie as well?
you mean the setup time?
No, I mean just in regular solve, how many seconds did you?
Oh, CG. I should have the number somewhere, but it's about 3, factor of 3. Oh, for CG it's more. I think for CG is a factor of 7 or 8, and for by CG step is 3. I'm going to show the comparison of CG by CG and MG in the next slide.
So wait, I just get my head around this plot. I see four pairs. Right?
Yeah,
So what are the differences between, say, the 2 pairs of reds?
yeah, yeah. So then let's just look at one group. Let's look at the green. There are 4 lines, kind of 4 groups. So these 2 are for the Hazen-Busch masses, and these 2 for the light quark masses. And because I do 2-step solves, so So this one is actually, this is the first solve actually. So you solve m dagger y equal to 5, and this is the second solve. So apparently the condition number is worse for this step, so it takes longer to solve the second solve. So I think this is,
makes sense because it's more complicated.
yes.
with normal.
Yeah. So you basically, yeah, I think this is quite interesting. So I just wanted to show you this.
But you do the same setup regardless of heavy or light. You're not doing more work for the
No.
light than the heavy.
No, I do the setup at the light quark mass.
Ah, okay.
Yes. So I don't redo the setup for the heavy. Yeah. Okay, so here's a comparison of the actual walk-off time for 3 different solvers, so for CG, BiCG STEM, and MG. And I break them down into light solves and heavy solves and the total trajectory time. So you can see for BiCG STEM, this is the solver that they originally used. And you can see they actually tuned the Hudson-Bush preconditioner so that the light solve and heavy solve are pretty balanced. So the time it spends in light solve and heavy solve are roughly the same. And for CG, it's a bit worse than by CG step. And for multi-grid, if you just look at the light solve, multi-grid, this is an average over 20 trajectories. So this is not just a single multi-grid solve with the exact setup on the gauge field and comparing it to CG and BiCG step. So this is an average over 20 trajectories with refresh every 3 trajectories.
Are you using the cryo basis, or are you just rerun CG battery?
Yeah, I just rerun CG. Basically, I don't reuse any.
There as well, I assume, for using cryo basis for subsequent.
Sure. No, there's lots of.
You did this, I think. This was your chronological
Yeah.
order.
Well, there's lots of the. This is. There's lots of
No.
improvements that go beyond this. It's
Right.
Just showing you.
Chronology would be a good apply to all of those.
What?
Chronology would apply to all of those things.
Yeah.
Right now.
No, I'm just saying that's the game that all 3 of those meant.
Yeah, you can do the same for multi-grid as well.
Yeah, sure.
Where was I? Yeah. So compared to CG, multi-grid, you gain a factor of 3, and compared to BiCG step, you gain about a factor of 2 for the light solves. However, the bottleneck is the heavy solve now because multi-grid doesn't really have any advantage over BiCG step. So overall, if you look at the trajectory time, you can see you for the 24 cube, you gain a little bit less a factor of 2 compared to CG and maybe about 50% compared to BiCG step. It's a bit better for the larger volume. So again, you can see multi-grid is 4 times faster than CG and 2 times faster than BiCG step. And heavy solve, you still gain a little bit, but not a lot. So in terms of the total trajectory time, here now you can see multi-grid gains a factor of 2 compared to CG, and a little bit, maybe about 50% compared to BiCG step. So I think this is already pretty good.
What is total time? The total time is not the sum of.
Right, no, because you have other parts like a gauge field force term as well. So you have other stuff involved. But you can see the fermion force calculations already dominate the total trajectory time.
Yes, but these other pieces, aren't they common to all methods? I mean, these extra pieces, I mean, what is the difference? I mean, these additional things that doesn't involve the total, are they fixed for all methods? Why do you have to take into account that?
I guess because there's such a small part of the total trajectory time, there's not much room for improvement if you really want to speed up HMC. Yeah. Okay, so this is just a nice bar chart showing the same thing as this one. So you can see the red is the heavy quark solve, which stays almost the same over 3 different solvers. And the blue is the light quark solve. So you can see from CG to bi-CG step to multi-grid, you have a kind of speed up over to the right. Okay, Rich made the point the other day that the performance of the solver can depend on the source vector, and this shows exactly that. So here I show 3 solvers, CG by CG step multi-grid, with either a point source or a random source. Okay, so let's see. The upper 2 lines are the time to solution for CG with this is random source and point source, so they don't really make much of a difference. However, for by CG step, this is very surprising to me when I first did this, because for the point source, you see by CG step, it's comparable to CG at heavier mass, but then it gets better for compared to CG. But then when you go to a random source, bi-CG step really outperforms CG by a lot, which I don't really understand. I don't know how to explain this, but this is what I found. And for multi-grid, it doesn't really make a difference whether you have point source or random source. So maybe some of you can explain this, but I don't really know how to explain this.
Well, this might be a place where you really want to look at the error as well.
I may find a different example, but it might be explained quite easily, I think. If I recall right, this is simple Wilson or is this Clover?
This Wilson, I mean,
This is also Holder Clover.
Sorry?
This is Holder Clover.
I don't know. I haven't checked. Yeah.
And is this even on preconditioned or is this just?
Even or preconditioned.
So I remember if you just use regular Wilson Islami without preconditioning on a point source, you actually run into numerical instability almost immediately.
Mm-hmm.
You end up with a reduced by 0, you need to look ahead by yourself, and I'm wondering if there's something like that going on.
Is this because bi-CG step is basically 2 chains coupled by orthogonality, and there needs to be some kind of overlap between these 2 chains?
Exactly.
And maybe because if you have a random source, we'll have overlap with both.
Yeah, could be.
I remember when I first did Wilson operator by CG step without even out, and then immediately, if you not realize I had to do a simple check by 0 in there, and maybe I didn't trigger that, and then it fixed it. I'm just wondering if there's something smoky.
Yeah.
I mean, there's also just the fact that a random source is likely to not excite low eigenvalues as strongly as a point source.
No, I appreciate that point too, but I'm just saying there might be some other simple step strangeness going on. It'd be interesting if this also held for other direct solvers, not by CG step.
Yeah, I mean, this is, if you like, bad news. The question is, how much does multi-grid improve a random source?
Exactly. So this is why you don't see as much improvement compared to CG in the previous slide that I showed the performance. So.
Well, I think the relevant test would be you take these configurations. Now we talked about the residuals and the errors test. You can observe, see which one is actually accurate. I guess you'd see large variations. You get
I mean, this is also regular computer.
what?
Not on the front of observers. I mean, the error, if you look at the error.
So now you have these gauge fields that you're generating, right? The question is, does the fact that you're not solving the system at all with CG affect your computation of the observer?
I think big one is this slide about reversibility, we get towards the
Oh, in terms of observables, I haven't checked like really more complicated observables, but I can get the same plaquettes, using CG by CG step or multi-grid.
So it's the wrong thing to look at. It's local if you want long distance.
Yeah, so I haven't really looked at other observables yet. Yeah.
So you're just looking at the forces. Be interested. Looking at how the fermion force
Mhm.
So looking at what's the L infinity norm of the force, all that things to account.
I think that the statement there, if I remember, like, it's try to do this sort of last year conditioning idea, like balance the force.
Yeah, but what I'm saying is that you get to the L infinity norm of the force, but using multiple versus versus simply taking out the force of G. Now you're on the blank road to those to be figured by using multi-grade or by using vice stat or using CG. You don't need to observe those. What is the force for the L infinity norm or the L1 or L2?
Mhm.
Yeah, I'm sorry. Last arrow is
But it's all online.
answer.
And we don't know the answer though.
That's the whole point. Yeah, but then one is correct.
That's the point. So it's much better. But it makes it multi-grid much more.
I think the assumption here is that both are converging reasonably well. I mean, maybe the assumption, but I mean, just the real question is why is one? Why do you get feel like this?
Yeah. So.
It's like four seconds. Oh, here you're going down to school.
Right. Yes. I'm almost done. So. Yeah. So. Because we reuse the setup from our previous trajectories, this will have the same problem as the chronological inverter because we want to make sure the algorithm is still reversible. So here's just some tests that I did. This is the action, the old action moving forward, and this is the action moving backward. And this is the difference between the two evolution directions. And this is one is with multigrid, and the other is without multigrid. So this is bisequence stack. So far, this is a very crude test, so I can't really see anything wrong with the multi-grid, but maybe more tests are needed to make sure that we didn't really affect reversibility. So future improvements, obviously, we want to implement it for Clover fermions. Right now, we just need to implement the Clover force term in fuel. And obviously, the most interesting question is whether or not this can be useful for lighter masses and larger lattices, because that's ultimately that's where multigrid will help the most. And as James pointed out, we can reuse the previous null vectors to save time in the subsequent setups. And so far, I only show the multi-grid performance with one level, and because the mass is heavy, so it doesn't really, it probably doesn't have much effect if you go to higher levels. But when we go to the lighter masses, we may want to investigate using more multi-grid levels. So, in conclusion, I think that is the test so far look quite promising. And it can actually further speed up the well-tuned modern HMC algorithms. So you basically can speed up on top of what you already have. And or you can rebalance the HMC algorithm so that you spend more time in the light clock solves. And I already said this, I think. So one pain in doing all this is that there are so many multi-grid parameters to tune, and so far we have to do it manually. It would be nice if you can have some scheme to do auto-tuning for the multi-grid. So I think this one ultimately we'll all need if you want to use multi-grid in a more efficient way. Okay, so that's it. Thank you.
Rich?
This is a question for someone, I'm not sure who, but I mean, would it be more interesting to apply this to RHMC algorithm, where would that require more light quark solves? Yeah.
So I was going to ask about that in a different way, because the point is, if you're going to do more than 2 flavors, suppose you're going to do a 2+1 flavor simulation, at least on the current GPU architectures, at light volumes, my bottleneck appears to be the strange quark piece, because it's a rational approximation. It's currently solved by a multi-shift system, and the shifts make the, you have something like order 10, 12 shifts, but your multi-grid algorithm will only gain you factors of 10 for what would effectively be the smallest of those shifts. So, and those smallest ones also generate the smallest forces, so you're not that worried about them. And so I'm finding, of the time spent in my force, I'm spending, let's say, roughly 80% of my time in solvers, and about half of that is spent in the strange piece right now. And so if I speed up only my light solves, I'm only going to be accelerating essentially a quarter of the run time. Is that right? So half of 80%, so 40% of my runtime I will accelerate. So if you think about that in terms of Amdahl's law, then that means you will have something like 60% left, which will limit your overall gain. Yeah. So I think it's fantastic that the 2 flavor pieces can get accelerated so well, and I think we should focus on also on better ways of doing the strange, which may sound counterintuitive because it's heavy and it should be cheap. But in terms of scaling, if you don't want to use multi-shift, what will you do? You can use a polynomial type approximation. How will that scale? Or you could imagine trying to do lots of single solves, but then how will you do that? Because you'll be working mostly at heavy masses, at which the gain from the multi-grid is less.
Yeah,
Does that kind of address some of your...
Well, I was thinking more of this nth root trick approach for even the light quarks.
Yeah.
Yeah, what about this nth root?
But it's still the same problem, right?
Yeah.
You still end up using a shifted solver because the nth root trick will employ a rational approximation for the nth root.
Yeah.
So you need to solve now depending on how accurate you want to compute your nth root.
Yeah.
Especially in the case of the energy, for the energy you will need. But you still need to use a multi-shifted system for every nth root.
Yeah,
the nth root is identical, unlike Hasenbusch, where the system is not identical for each one. Once you do the setup for one nth root, it's the identical setup for every nth root. So it changes it into a multiple right-hand sides problem rather than having a different setup for each rate determinant ratio. Yeah, so maybe what you want to do is have a setup for each shift.
Well, I'm saying is that
I don't know.
No.
Well, why does a multi-grid work for?
Right. So we need fast solvers for any parts.
Yeah.
Well, of course, I mean, in yeah. Of course, if we go to very fine lattices, all quarks are light. I mean, this may be, way in the future, right? I mean, if you really want to go to large lattices, 500 aside, then everything's going to be slow, and then it'll start to be important.
There's one other comment maybe just related to slightly separate. I get this job. So the other thing.
Because our one remote viewer will not be hearing it.
Oh.
Or also somebody viewing it after the fact.
So another thing that comes to my mind is one of the things that we started doing recently as we go to the bigger lattices is to consider using higher order integrators. Yep. And with higher order integrators, unless you use the force gradient one, which we don't have yet for Clover in our code, we are used to use these integrators that have 4 or 5 force evaluations per step. And then making a recursive multi-timescale integrator out of that is not easy, because at least if you do it the sort of standard recursive way, for every time you recurse, you will now be doing another 5 solves. So it's not that straightforward to separate your timescales if the costs in the various forces are not factors of 5 or 6 different. So you might be more in the situation where you have more and more of your action pieces on a single time scale, gated by the one which has the largest force on that time scale. And so that can also affect how much benefit your multi-grid can get you. It might actually help you, because now you might end up doing more of those light solves than you want, because you can't effectively multi-scale it, because you have to do 6 sub-steps instead of 2 sub-steps, and the factor of difference isn't a factor of 6 bigger, so you would lose if you did that. So now you're going to keep them on the same scale potentially, then you might get a bigger benefit.
You need to recalibrate everything.
Okay. I have 2 questions. I guess one is, you already said because you're reusing setup, you're already sitting with regard to reversibility, so why not do chronological inversion from the get-go?
We can combine chronological inverter and multi-grid.
Okay, but then I guess one problem, the problem that Hanta was looking at was, if once you do chronological inverter, you're forced to do much more accurate solves than you would have to do if you just turn chronological inverter off and still want to maintain reversibility. Is that true here? Are you forced to do accurate solves?
Yeah, actually that will help multi-grid, because if you need tighter residual, multi-grid may gain more compared to CG.
Well, I mean, relative to without chronological inverter and doing an inaccurate solve.
Probably the other way around. If you want to do multi-grid, you better use chronological solves. You have to solve more accurate anyway. So
Right.
do it as
Right, exactly.
as good as possible.
Yeah.
Right.
Do none of those.
So I guess then the other question, and maybe I don't understand. You do the setup for the light Hasenbusch term, and then you reuse it on the heavy. But the heavy's a bottleneck. Is there any advantage to doing a separate setup for the heavy?
No. You can basically use the same setup for all different masses, at least for wheels and fermions. That's the case.
I mean, not entirely true. I mean, the red-black preconditioner actually screws up the setup for the heavy.
Not for Wilson, for Clover.
No, the setup works if the mass change is just a translation of the operator. But if it isn't, then your eigenspace is really changed. So your eigenspace changes in a red-black. When you change a mass in a red-black preconditioned operator, it's a different operator. It's not just a translation of the operator. So that actually means that you might not want to use heavy masses for Hasenbusch. You might want to use a fake mass parameter, which is just translating the red-black operator. And there's actually no reason not to do that. What? No, after you've done red-black precondition?
Yeah.
Even in red-black?
1 minus kappa squared dg. Kappa squared is a shift.
Yeah, m squared minus dd dash.
Okay, all right, so it's only in Clover.
Yeah.
Okay, so when you get to Clover, but then I say, why in Clover, when you do Hasenbusch, why not do a additive term to the red-black operator? Who cares? It's not a mass. It's just a preconditioner.
Actually, yeah.
There's no reason to call Hasenbusch a mass.
So I tried at one point. It's been done too.
Yes, of course.
Yeah, James and I actually talked about this.
you have
how to, that's one way of
Yeah.
doing the Hasenbusch, yes.
You tried
we
it?
actually thought about it.
So I've tried at one point. I've tried at one point to just shove on a twisted mass term at the end of your Clover operator, so that when you form the square operator, it ends up being spectral cutoff. Just for Hazen-Bushing
Yes.
kind of thing. One downside is you can say bye-bye to BiCG stab right away.
That's multi-grid as well.
Yeah.
No. For regular one-grid twisted mass.
Well, why use twisted mass? Just a
So
mass.
multi-grid only works in light quark mass for twisted mass. It doesn't work in quark mass.
Because
It's a large twist.
the reason it had a slight twist in it, yeah.
Why put a twist in? Just
The reason was that when you did M diagram, it would end up as being a plus mass thing.
Yeah. But you can
So-
just add a plus mass. M diagram.
You get cross terms then.
What?
You get cross terms then.
Oh, the M diagram, add a plus.
Right?
It's
Well,
the same as having a twisted
it's the same as adding a twisted mass to M, right?
Oh,
in N.
okay.
Yeah. So BiCG stab immediately started diverging, and I said, okay, I'm not going to save much
Well,
with
you
this.
don't want to use that. Does that
I think that was the question. I think I asked my 2 questions. Okay, any more questions? Oh,
Ask because in this test you said that you start from a thermalized configuration. What happens if you start from like a random or cold start? Or why actually you choose?
Yeah, then the comparison is not as meaningful because you will ultimately spend most of your time doing the thermalized configurations. So, yeah, I mean, eventually we will start from the cold start if we really use multi-grid in the production. But then, you know, the majority, what we really care about is how much time it takes to do the inversions on a thermalized gauge configuration because the majority of the ensemble will be thermalized.
The line modes, random initialization, the line modes will be present until you thermalize. And so the speed up of multi-grid is small. It'll be like doing heavy quarks all the time until you thermalize. You expect the speed up just to get more as you thermalize more.
okay. Good. So just on the scheduling note, we'll do Abdu next, and then we'll have our break, and then we'll do the last 2 talks, unless somehow Sergey shows up at the last minute, which it doesn't look like he's gonna. So, and then we'll break for dinner. Okay, let's thank our speaker. Okay, let me switch the talk. And is your mic on? Yeah, I think so.
It is on?
It is. God, my eyes. I turn it on. There we go. Good. Okay. So now we have Abdu, who I first met at the last time QCDNA was at Yale, and all-mode averaging with approximate eigenvectors and twisted mass.
Thank you.
I
Yeah.
hope you will explain what all-mode averaging means.
Yes. Yeah.
This nomenclature, I think, confuses everybody.
Okay. No, I mean, I explained it as much as I understood from the paper, but of course, I'm sure there are people here who knows it better than I do. So, yeah. So this, I mean, forgive me if there are more details than needed in here. It could have been let's say more concise, but okay. So we can skip the extra details. So this is, yeah, I would like to talk about this all-mode averaging with approximate eigenvectors applied for the twisted maze. So first I will review what is all-mode averaging, and then I will talk about how we can do it, or is it possible to actually do it with approximate eigenvectors applied to the case of twisted maze fermions. So this work, again, I'm sorry I'm flipping here. So this work is done at the Cyprus Institute with Dina Alexandrou and Yannis Koutsu. So this all-mode averaging, there is another thing that goes with it. It's called covariant approximate averaging. The idea here is given a specific number of gauge configurations, we compute observables. How can we reduce the error in these observables given this specific number of configurations at a low computational cost? So the idea here, or the approach that's used, is we look at the symmetries of the action or the correlation functions to increase the statistics. And the second ingredient of this approach is we use it, not we, the authors. By the way, this is Igor Shintani et al. In this reference, is to use what's called all-mode averaging to reduce the computational cost needed to implement these symmetries. So then here comes the name covariant approximate averaging. So the method has been shown in this reference to be applied to many observables to lead to good improvement, reduction in the error, and tested on domain wall fermions with 2+1 dynamical quarks. So again, as I said, so the covariant averaging is if we imagine that this O of U is a gauge configuration, O is some correlator we calculate in the lattice, the nucleon propagator, for example, or 3-point function, let's say. And we imagine that we have a symmetry of the action. And in this particular case, my understanding from this paper actually is most of the discussion goes into translational invariance. So this is the idea. So basically we have this gauge, we have this group of transformations, which means we make a translation of the coordinates. So our configurations will transform to UG of X, which means U at XG means the gauge field transformed to these new positions. And the transformed correlation function is defined here that it will be the correlation function on the original gauge configuration, but at shifted locations. So basically, what is being said here is, let's say we calculate 2-point functions and we choose the location of the source for these 2-point functions, but we know that we can do the same. We can get the same physics if we choose different locations of the sources. So this eventually statistically will give us the same average at the end. So because G is a symmetry, then the expectation value of this operator transformed correlation function is the same as the one computed on the transformed gauge field. And because this transformed gauge configuration has the same probability weight, because the action is invariant, then this expectation value is the same as the original one, in other words. So it's just simply what I said before. So now, if this expectation value on the original gauge is the same as the expectation value on the transformed gauge, configuration by configuration, then trivially we can perform the sum over all possible transformations. So the idea here basically simply means, in my own understanding, is, let's say, if I shift the source and calculate the correlation function, or keep the source location and shift the gauge configuration in the opposite direction, we should end up with the same number, identically, on each configuration. So, like I said, from here, we can add over all possible transformations, which means on the lattice, we can choose any source location that we want. So that many of these would, typically, we're not going to do all of them, but okay, I can choose subset of these, and I make the sum, and these two are equal. And then we define basically our correlation function to be an average over all of these. So basically, instead of calculating on only choosing one source location, you do 100 source locations, right? So this is everybody know how to do that. And the question and the important point is your expectation value that you get with this summation is the same as the one that you get if you only choose one source location, for example. And but the difference is the error in this O sub G is that the error is, of course, is much smaller by a factor of 1 over square root of NG here, which means the number of source locations that you have used in the calculation. So that gives you an improved statistics. So yes, objections. Yes. Yeah.
I mean, this factor 1 over square root of n, of course, neglects any correlations between.
Yes, exactly. Yeah, I was going to say that. Yeah, that assumes that there is no correlation between these source locations that you have used. That's true. Yeah. So, but the new thing here will be that we know how to do this, but every calculation we'll do will be at the same computational cost. So, how to reduce the cost of this calculation to make it less expensive? So this is the key point. So reducing the cost here will mean that instead of using the exact correlation function for this transformed correlation function for OG, we use some approximation. We use an O approximate of G such that this covariance still holds. So this is an important point. So we're not going to use it exactly. We're going to introduce some approximation, and we make sure that this approximation, to a good degree, resembles the original correlation function that we are interested in. And of course, similarly, we do this because O sub capital G is just the summation over all these little g's or all the elements. So basically, we replace this summation by the approximate as well. And from here, we will define an improved estimator. So this is our improved estimator, which is basically your correlation function that you started with minus the one, which is the same. Let's say I like always to think in terms of, let's say, a source location that we choose on the lattice. So this is for, let's say, you choose some source location. This is the one that you, your approximate correlation function for the same source location, plus this O capital G, which has a summation over many other source locations. So the point is, this expectation value of this improved operator or correlation function is the same as the expectation value of your original correlation function O, when the expectation value of this O approximate is the same as this O sub G. So basically, you subtract something and you add something, and you hope that that these expectation values will be equal, so they will cancel, and you will end up getting the same expectation value of your original correlation function. But as the key point is, this operator now should have a smaller error because it includes these other many transformations that we have done. So the error in this improved estimator is, you can show, or the authors have shown, that okay, it's given by this expression. So sigma is the error that you will get from your original estimation with only one source location, for example. And these R and capital R measure the correlation between your different measurements on the lattice. So this capital R is a correlation between different various source locations that you have chosen. While the R without any subscript means the correlation between your approximate operator and your original operator. So this is the point. So now here, ideally what we would like to have is that our original error gets reduced by a square root of ng, which you just mentioned. So for this to happen, what we will need to have is that this delta R is the deviation of R from 1. So we would like this to be as small as possible. So as long as this will become smaller, and your capital R also, this summation over these correlation functions for the various measurements that you have done is also, okay, this doesn't show anything. Doesn't work? Oh, I'm not sure. Can you shake? Before. There's another one? Okay. Oh yeah, okay. So, I don't need it. Okay. So as long as these correlations are close to 1, means then what you will get. I'm sorry. The small r has to be close to 1. The capital R has to be close to 0. Simply stated, that your approximate operator or correlation function has to be very much close to the original one that you started with, even after you introduce this approximation, and the correlation between the different measurements that you will do should be as small as possible. Okay, so on the laptop. Okay, yes. No, delta R close to 0. R close to 1. Delta R is just R minus 1. Yeah. Yeah. Okay. Means your approximate operator that you have built and your original operator are very close. They are very close to each other. This approximation is not just nonsense. It's something that really close to your original thing. Okay. So. Thank you. Okay. Yeah, okay, so the extreme cases, like I said, is R equal 1, which actually means your approximation is identical to the original, and the correlation between these two measurements for different transformations is 0. Then your error will get reduced by square root of n measurements that you have done. The other case is your approximation is nonsense. It's not related at all to the original correlation function that you are calculating, and your measurements are very much correlated. Then actually you could make things worse. You could get a higher error. Okay, so these state some criteria for this method to work, which simply is very much what I've said before to get the error reduced. So which I'm not going to go through all of them, but basically what I said before. So the question, of course, after that is how we build some approximation to this correlation function. So two approaches. One is what we call low mode averaging, and the other one which is all mode averaging. So what are these? The low mode averaging, which we are not discussing here, but it's basically your correlation function is built upon a propagator. And your propagator here will be approximated by a sum over low eigenmodes that you have. So if you replace directly replace the propagator S by this spectral decomposition of the low eigenmodes, then and you use this to estimate your correlation function, then this is what we call low mode averaging. And this works for some observables, but it does not work for all, and also it works at some time shifts or time locations, not for all time locations. So in this sense, it's limited. I'm not going to go further than this, because what we are interested in is this all mode averaging. So the idea of all mode averaging is the following, that your propagator is built out of two pieces. The first piece is again, the low eigenmodes of the Dirac operator computed to a high precision. That is the first part. And the high modes of the Dirac operator are approximated by a polynomial of the Dirac operator itself. So this is what we call all mode averaging. So your propagator S acting on some source B will be given by basically the contribution coming from the low eigenmodes plus the contribution which is described by a polynomial of the Dirac operator. This polynomial to a certain degree, which is basically the CG polynomial. So you do some iterations of CG, which equivalent to some polynomial with some coefficients. Of course, we don't know explicitly what these coefficients are, and if at the end you get an approximation of the propagator, and you plug the operator in the propagator in the correlation function, and this is what you call your all-mode averaged correlation function. Now, this is okay. In a sense, this could be very much similar to any of the deflation methods or multigrid methods, or I mean, so basically, you try to approximate the low eigenmodes to a certain degree, and then the high eigenmodes you get from your preconditioned solver. However, here the way it's described in the paper is that it requires using these low eigenmodes to be computed to a high precision, and the understanding is this to some degree guarantees that there will be no bias of your correlation function. When you calculate these to a high precision, then you know that your correlation function will not have a bias because of these eigenvectors that you introduced here. So in practice, basically this is how it works. Like I mentioned, you project over, you calculate some low eigenmodes exactly. Your source is projected, or let's say these modes is deflated exactly from the source. That's where your this is where your exact eigenmodes come useful, and then you solve the projected system with CG, which gives you the high modes that you didn't account for, and this is what we call the. And then of course, then after that you take this solution and you use it for your correlation function. So, has been tested, like I said, on many for many observables in these 2+1 domain wolf configurations from the RBC collaboration, 24 cube times 64 lattice, and for 2 pine meshes, 330 and 420 MeV. For example, I'm just showing here an example of the axial charge of the nucleon, GA. So on the left, what we see, the plots we see on the left are the ones that one computes on, let's say, using one source location, and just what would one do to calculate this correlation function. So this is what we call the original approach. And then in the middle, we have the low mode averaged method, and on the right, we have the all mode averaged method. So on each of these plots, there are these blue circles, which is GA itself with its error, and we can see very well that this is actually, this all mode averaging method gives you a very small, much smaller error. And then the same thing you see, the upper is for the lighter quark mass, I'm sorry, yeah, and the lower is for the heavier quark mass. On these plots also there is this red and green curves. The red is basically this is the deviation of the little r from 1, which is delta r, that we would like it to be close to 0. So in this case, we see in all mode averaging, this is very close to 0. And the green is the sum, it's a capital R, which is the correlation of the different sources that you have used to do this calculation. So also we need this to be small. Okay, so the question actually that we were interested in is basically, can we achieve this gain in the error reduction also using some approximate eigenvectors, not the exact ones that was used here. So now the two main questions is, does using approximate eigenvectors introduce any bias in the correlation function that you calculate? Now, whether can one combine the computation of these eigenvectors with the computation of the correlation function? Because you calculate the correlation function, you have to do inversions, and in the all mode averaging, as it is described, you have to calculate these eigenvectors up front, and then use them to, to solve for the sources that you are using in your calculation. So the approaches that one can envision here is incremental IXCG, which is the main interest that I'll in this talk. But the same thing can be the situation for things like inexact deflation with domain decomposition, or the way multigrid works with this near kernel subspace that's used. So because all of these is supposed to give you a mix of eigenmodes that are approximate to different degrees. So how does this affect your calculation if you apply this method? Now the issue of the bias is that in the case of exact eigenmodes, you assume that there will be no bias because these eigenvectors are accurate to a high degree. Of course, exactness here doesn't mean to machine precision. It means to some tolerance that is hopefully higher than your linear system solve. Yeah, so now how do we, and again, these eigenvectors, it was computed in a separate calculation independent on your source solve. So this separate calculation also gives you a guarantee or some kind of confidence that there is no bias because they are not related, the calculation of the eigenmodes versus the solutions. So in case of let's say domain decomposition methods or multigrid, these approximate modes also are computed separately in a setup phase, which in a sense gives you some kind of guarantee that there will be no bias. In the case of incremental IXCG, what usually happens is that we combine the computation of these eigenmodes with the solve. So in a sense, this is good because this gives you more efficiency in computing these. You don't have to do a separate calculation for that. However, how does this affect your final result in terms of introducing some bias? So in this talk, like I said, I will focus on for incremental IXCG. So the first approach, of course, if you want to avoid the bias, is to say, I will do the computation of these eigenvectors separately in IXCG as well. So I will do the same thing. So what I will do, I will start the calculation, take some random initial guesses that has nothing to do with my source locations, do some of them, collect some approximate eigenvectors, and then do the rest of the calculation. That's one approach. The other approach, which I personally think is better, and I think it's also correct, is that actually we can do the same. We can do simultaneous calculation of these eigenvectors with the solution of the sources that we are using, and at the end, the solution that we get is a solution. I mean, because at the end, whether you do deflation or whether you do multigrid or bi-CG step or CG, one will end up with a solution, right? So that's accurate to the residual that you are looking at. So why would this solution be different from, or how does this solution can remember exactly how do you reach it? So at the level of the accuracy of the calculation, I think one can claim that the solution, if it's accurate to a certain level that you choose in your calculation, then it shouldn't introduce any bias. So that is the thing. So this is what I'm trying to test here, or we are trying to test here, is to look at this second option, because like I said, it's mostly cost effective. We can do all these calculations together. So I apply this to twisted mass action at maximal twist. I don't go too much detail, of course, but okay, in twisted mass, quarks are introduced as doublets, and it has a nice property that automatic order improved of the correlation functions. But as people also pointed out, that for twisted mass, bi-CG step actually fails, doesn't work. However, CG works, and consequently also IXCG also works for twisted mass. It has been we have tested that and implemented this in the twisted mass code. So I'm just showing some sample results here. So for example, this is a 2-flavor configuration at 24 cube times 48 at 300 MeV pine. These are the parameters used for incremental IXCG, and this is the time to solution as compared to the case of CG. And we see that the time of solution really decreases very nicely as we increase the number of right-hand sides that we solve here, with some small overhead in the initial phase. this is also a test for the 2+1+1 configurations on a larger lattice at a lighter pine mass. Actually, and I will use also this in the tests that will come later for this all-mode averaging method. So in this case, also we find a very nice speed up for the IXG in terms of the time to solution as well. And finally, this plot is from a recent simulations at actually the physical pine mass on a 48 cube times 96 lattice. And in this case, these new simulations are done with twisted mass plus a clover term. And here, it's much harder problem, actually. So IXG it's not as efficient, but in this test, actually, we didn't do a lot of testing in this because I'm just showing here deflating 150 eigenvectors, and I needed really a large subspace to generate some of these 150 eigenvectors to some reasonable accuracy. So that need to work to be done at this. But I mean, in these other lattices, it works reasonably well. Okay, so now I show the results for this testing. So here I use an ensemble which is a 2+1+1, 48 cube times 96 at the pine masses around 200 MeV over 232 configurations. So the way we do this test is the following: that first we do 12 source inversions to a high precision, 10 to the minus 9, which I label these by HP inversions. And for the same 12 sources, I will do a low precision solve, which is only up to 10 to the minus 2. And then additionally, for additional 72 source locations, I will also do a low precision. So this is like what we were talking about in our improved estimator. So our improved estimator will have 3 pieces. One is high precision here from 12 source locations, and the other one is for the same source locations with the low precision, and then the extra source locations will be done to a low precision as well. So the time locations of the sources were not completely random, although the special positions were chosen to be random and hopefully not correlated. So our improved estimator will be given here by this expression, which is very much the same as I did before, but instead of using only one source location, here I use 12. So this will be 12, 12, and this will be the 72. And this estimator is divided into like 3 pieces. This H0 is the high precision, minus L0 is the low precision with the same number, for the same source locations, and L1 is the 72 extra source locations that we have done here. So, and what we'll take this for different quantities, basically the nucleon, the rho, and the pine masses, and we look at how they behave with this approximation. So, I will look first at the nucleon. So this is this plot is 1 minus R, which shows how correlated my approximation to the original. And we said that this we like this to be very small, close to 0, ideally. And this is as a function of time. And we see actually it's very reasonably small. And of course, it increases a little bit as we go to the middle of the lattice, but it is small still. So this plot is the effective mass plot for the nucleon mass. And here we show all the pieces that comes into the calculation. So H0 is which is red here, is a high precision, which means if one does only high precision. L0 is the one for the low precision, and L1 is the 72 extra sources, and the final result is this black star here. So if we take these and put them together in this plot, so this is what we see. So this is only high precision. This is a piece coming from L0. This is a piece coming from L1, and this is our final estimation. So like our final result should come from the red minus the green plus blue, and this will be our final result here. So the hope is the following, that this will be more precise, so there's a smaller error, so which it is, have a smaller error than our only high precision value, and that these, the green and the blue, should cancel. Otherwise, we'll introduce bias in our calculation. So, and within errors, they really seem to be canceling. So, and our final result is very much consistent with the one that we get if we only do high precision for these sources. So, yes, sure, yeah.
So the red one is what you call your original operator.
Yes.
The green is your full props.
Exactly.
And the blue is the full props.
Yes. No, no, no. The blue is there is a O sub G, right?
O sub G of props.
Yes.
Does that include the 12 that's already?
No. No.
So okay, so you're excluding those.
Yes. Okay. Yeah. Yes. Okay. So next thing, I look at just this plot which shows how the this CAA effective mass for the nucleon behave as one increases the number of low precision solves that the 72 sources that I have done, and we see that actually, I mean, we see the errors getting smaller, and as well is staying consistent with the one that we get only from the high precision. So I think this is for the nucleon. So the final plot we look at is how is our error, the improved error in our improved estimator, how is it behave as a function of the number of low precision solves? And as we said, that this is ideally will be like goes like 1 over square root of the number of low precision solves. So the stars are the actual numbers, and the solid is basically the 1 over square root of the number of low precision solves that we did, and the red is fit to these data, which comes to show that actually this correlation is very, very much close to 1. So it works very well as well here. So we have a very good correlation, and then our errors basically goes like 1 over square root of n. So we do the same thing now for the row meson, and here the results also have the same trend. So this is the high precision. Again, this is O approximate, like you mentioned, and this is the other piece coming from these 72 sources, and these should cancel without introducing bias. And our final numbers here, which is consistent with this number within error. And the same kind of plots I show like for the nucleon. This is a evolution of this row mass. And again, the correlation also goes like, I'm sorry, the error goes like 1 over the square root of n low precision. So for the pine, because pine is very accurate, so actually we didn't find that this this all-mode averaging in this situation to actually improve the error of the pine. So it was not, there was no big improvement here from using low precision as well. But again, I show the same kind of results. So these results are, I mean, not the whole story. This is not all the tests that actually we would like to do for this kind of approach. So we plan to do more testing as well to see, for example, if we do this IXCG with a random source, with random sources to calculate the eigenvectors, how the results will look like. But at least for this, for just a straightforward calculation, it doesn't seem to indicate any kind of bias in the numbers, which is actually was encouraging. So my conclusions that this all-mode averaging method are efficient for reducing the errors, the hadronic observables. IXCG worked very well for twisted mass. At least not at the physical pine mass, but so far worked very well. We tested how to combine this deflation with this all-mode averaging method, and we found that there is no bias introduced with these approximate eigenvectors for the observables that I presented here. And
Okay, do we have any more questions? Okay. For the remote, you guys have 5 remote participants.
How much extra time did it take to do those 72 sources? Because it costs you some time, even though you're approximating it to a lot less precision.
I don't have the
Uh-huh.
it's much faster. First you do like 10 to the minus 2, okay, versus 10 to the minus 9
Mm-hmm.
for the high precision. And also when you do the deflation, so basically I have deflated, when I did the high precision, I made the deflation already. So this was actually very fast. I don't have the data before me, but
Okay.
it's very small.
And then just to follow up, so you do 72, but you can in principle keep going. And
Yeah.
I would imagine that you stop once you start seeing that it's the gauge fluctuation rather than the operator fluctuation that starts to dominate. And you should flatten out as you increase the number of the number of
Yeah, what usually happens is when you do more source locations,
Mhm.
after sometimes these become correlated. So let's say you do 72
Sure.
sources or 100 sources, but if you do more, maybe if you do more, it doesn't really help a lot. So after some point, the correlation between these source locations chosen like stops you from getting any.
Yeah, I guess my thing is you don't know it until you actually do it, right? So how can you say I'm going to stop at 72 or 100?
Right.
You know, so that when you do future calculations, you kind of.
Okay, how to do that? I'm not sure. I can't
Okay.
think of maybe somebody else has a.
Somebody from RBC.
Yeah.
Well, it's actually a tuning problem. So the number of exact solves you have and the number of sloppy solves, as Taco would call them, is a tunable parameter, and also the precision you use. And in the end, everything will depend on the observable you are studying. As one guidance, I would try to think of what kind of sources do you use? Do you use a point source, or do you use something smeared extended source? So that may give you some indication how many sources can you put on the lattice. But this is a general problem. People in the past also tried to put more than one source per lattice, and then they put them only in time direction, and later they also used the spatial components, the spatial directions. And of course, once you saturate the lattice and you don't get any statistically new information, they are correlated and you don't get any information. So I was surprised that you used 12 exact solves. That's a relatively high number compared to what RBC used in the past.
Yes, I think because I can use exact solve as many as possible to actually see if there's any bias. The idea is to check if these calculation with these approximate vectors give you any bias. So hopefully if you more exactly just to make sure to see some. Okay.
Well, the only way, if I understood Taku correctly, so you can forget about deflation. You can just do it with a regular CG. That simplifies the problem, and you don't have to. Yeah, you have just less components.
Yeah.
And if you do this with CG, Taku says that you should fix the number of iterations to avoid getting a bias. If you would go down for reaching a certain precision, you would do a different number of iterations for the different sloppy solves, and that could technically lead to a bias, he says. But also that bias, he argues, is very small. I haven't followed deeply enough on that to comment whether this is correct or wrong.
Yeah, I mean, actually, it was in the slides, but I skipped that. Whether you stop at certain number of iterations or you stop at certain residual. With the residual, you go from one source to the other, probably give you a different number.
So the way you measure your bias was that you looked for observable, the error bar was out improved and the error bar, and you saw that was overlapping?
Yes, in principle, yes. But I think that's why I said this is the beginning of this test.
Mhm.
It's not a final thing because ideally what you want to do, you do, let's say, the same number of sources all to high precision and see what you get, and then you compare with.
Sure. I could also say that, you know, that since they're on the same configs, you can do a jackknife difference to see if the jackknife difference is statistically different from 0. And that should, you know, I mean,
Yes.
get better.
Doesn't call it a bad one.
If you don't worry about the sources being correlated, you just take a sum and you can't do anything wrong. If you try to do some jackknife error estimate, then it may get dicey if you want to propagate the uncertainty you estimate on the configuration and then thinking of what you do with this over the entire ensemble of different configurations. So I don't know what you want to do with this. So you could technically do some study and check whether these things are statistically correlations or what the correlation length is on one configuration. But you may also just say you average that and don't vary.
Okay, any more questions? Good, so for our remote participants, we're gonna have a coffee break now for a half an hour, and then we'll pick up with the schedule. Great. Okay, so, and we do have a reservation for Thali too at 6:30 for 12 people. I think if there's a few more, it won't be a problem. Okay. Great. Oops. Okay.
It's loud. So this goes
Yeah, let me
forward.
make sure it's on. Okay, laser, and change page. I have no idea what the button, that's probably mute, so don't use this. Laser, and change page. Sure. Ready to go?
Okay.
So don't worry about the time.
Okay. Yeah, it'll be very brief.
Well, if it takes, you're fine. Okay, so, I have Reed C. Lee, maybe. I guess you're a graduate student with Steve Gottlieb at Indiana. Okay, on staggered D slash on phi. Okay, go ahead.
So I'm gonna talk about the staggered D/Flash code performance on the Intel Xeon Phi architecture. So I'm gonna give a brief background on the Intel Xeon Phi night corner architecture, and I'm gonna go on with the staggered conjugate gradient performance on with the MPI and the OpenMP parallelization. And I'm going to talk a little bit more about the vectorized staggered D/ code on mic with the data. Oh, I'm wondering if 14. I'm wondering if this is okay. Is this better?
Maybe put it on the right side.
Right side. Okay.
How about this? So including the data layout and the dispatch performance on one mic card, and then conclusions and the work in progress and the to-do list. So this is a nice picture of the mic architecture, showing that the card is a symmetric multiprocessor on a chip. So it has like more than 50 vector cores, and they're connected with the bidirectional ring, and also with connected with that with the DDR-based memory, and it has the each core has the coherent cache. And so here are some numbers. So the on the 5110P, that's a version of the chip. It has 60 cores, 4 threads per core, with a CPU speed 1 gigahertz, and it has 512-bit width of the vector processing unit, and with the maximum bandwidth 320 gigabytes per second, and it's connected with the processor by the PCI Express bus. So what we did first is that we ported the mail code version 778 straight to the mic card, and so it can be parallelized with the MPI and the OpenMP scheme. And we run the code natively on mic. That means we run everything on mic, and we didn't do nothing, none of the work on the processor. That is to save the time of transferring the data between the processors and coprocessors. And we use the double precision in our code. So the memory usage in the conjugate gradient routine, in this case for the multiple mass conjugate gradient inverter, it's like this. And then we use the staggered HISC quarks, and the flops per each conjugate gradient iteration is like this. So number of quarks masses is the number of masses, or number of quark masses that we use in the inverter. So so we observed that from the benchmarks, the conjugate gradient speed on one mic card with the multiple mass inverter, which we use 9 or 11 masses, and around the 50 iterations. So with the MPI parallelization, the speed is around the 12 to 15 gig flops, and it peaks at L equals 6 or 8. So L is the lattice size per on each dimension per MPI rank in this case. And when we use the OpenMP parallelization, we observed a performance of 15 to 20.
So what is that total lattice size?
I'm sorry?
The lattice size is like single to the 4?
A lattice size, okay, so we use different lattice sizes. So we test L equals 4, 6, or 8 up to 10 or 12. So this L is the lattice size on each dimension per MPI rank.
Yeah, you have 12 MPI, right?
I'm sorry?
No,
we use the weak scaling benchmarks.
No, I'm just trying to understand what is the global lattice size you put in the mic. Like, how big is the lattice? Like, in every direction?
In each direction. Yeah, this is the lattice size in each direction. So it's like.
So is it 6 to the 4?
Yeah, right. Sorry.
Okay. How many of the cores?
We use the okay, so we use the like tested like 50 MPI rank, so that means 50 cores, right? And then 60 and up to 240 MPI ranks. Yeah. So and we also tested the using the OpenMP parallelization, and so the performance is a little bit better than MPI, and it peaks at L equals 6. So this L is the lattice size on each dimension per core.
The first thing only get MPI.
This is the MPI only without. This is only MPI, so it's not OpenMP. And the second one is OpenMP only. Yes. And then we got some stripped down code from the Professor Datar, and he tested the single mass inverter with the OpenMP or 60 cores, and he used a lattice size of L around 8. And he also used more iterations, like 600 or 1,000, and he observed the speed of up to 45 gigaflops. And when we try to weak scale the code on multiple mic cards, we observed a very, the code performance didn't really go up. So the total performance gain is, is less than 20%. And we use the Intel MPI for communication between the coprocessors. Then we try to vectorize the staggered D/ code, and the code is based on the Wilson D/ code from Berlin and some Intel staffs. So we modified their code, and we tested the naive D/ and the D/ with the naive term. That means the link of third neighbor, between third neighbor. And then we run this code on one mic card with 59 cores and OpenMPI. And also, so there were some options that can potentially affect the performance. So first is the compressed gauge field storage. And the second is streaming store for the staggered fermion output fields. And the third is change of the SOA length and how the lattice are being assigned to threads and cores on each OpenMP loop, and something. So I'm gonna explain this in the following slides. So the data layout, we use a single precision in our code, and in this case, the vec length equals 16. So the vec length here is the number of floating points instructions that can be processed simultaneously by the vector processing unit. And we follow the structure of arrays layout. That means that we put together the fields that's located on the lattice sides with contiguous x indices, and we put that in store that in an array with the length of SOA length, and it can be set to 4, 8, or 16. And also, when we transfer the data to cache or to the vector processing unit, besides the SOA length of structure of array, we also aggregated store data in aggregation along the y direction with length of vec length divided by SOA length. So so in this case, that the total number of data that's grouped would be of length vec length. And the lattice size has to be the SOA length times n in x direction, and the vector length divided by SOA length times m in y direction. So n and m are integers. Here's a picture of explain this the data layout in the cache or in the vector processing unit. So this vector length is 16, and the SOA length is 4 in this case. So we see that in x direction, there are 4 data that's stored contiguously, and then followed by the y direction increased by 1 and by 2 and by 3. So in this case, we have the staggered fermion fields stored in memory with the structure of this 3, that means 3 colors, and the 2 is a real and imaginary part, and then the SOA length, it's the array. And then in cache, instead, we have the back length data instead of SOA length, as we have saw in the previous slide. And so we compare this to the original milk data layout, which is a complex structure of 3 color indices. And we can also enable the streaming store. So when we do streaming store, it means that we only write to the memory that without reading them first. So in that case, we can save the time of reading those data, which are maybe in some cases really not necessary. And in that case, the SOA length can only equal to 8 or 16. It cannot be set to 4. So, and similarly, we have the gauge field stored in the memory, which so we store gauge with 8 directions, so backward and forward. And then this growth here equals 2 or 3. So when it equals 2, it means that we use compressed gauge storage. And when we use that, we rely on the fact that the gauge field is the unitary gauge field. So the third row of data can be constructed from the first 2 rows in the calculation. And then 3 columns, and the real and imaginary part, and then the back length or the SOA length. And also the original milk data layout for the gauge field is with the 4. It stores the 4 forward directions, and with 3 columns and 3 rows and 3 columns. So with that data layout, we tested first the naive D/ performance on one mic card with the OpenMP, and with compressed gauge, we observed the performance around 190 gigaflops, and with bandwidth is around 140 to 150 gigabytes per second. And then with the staggered phase, we didn't see much performance difference for that. Well, we're adding a staggered phase. And when we use the uncompressed gauge, that means we store all the 3 rows and 3 columns of the gauge field in memory. The performance went down to 140 gigaflops, and the bandwidth went up a little bit to around 150 to 160 gigabytes per second. And we also tried vectorized naive D/ code with the original milk code data layout, but performance was lower. We observed typically around 50 gigaflops. And we saw that the speed increased slightly with increased SOA length, but they are not very obvious. And we also so paired with the adding when we add the stagger phase in, we also need the rephase routine, which calculates the naive link with the stagger phase. And we see the performance is around 20 gigaflops, and bandwidth is around 170 gigabytes per second. So the performance is low because we don't really have many floating point instructions compared to the slash routine. So this is a table showing some detailed data from our results. So we tested on the lattice size of 32 qubit times 128. And so when we see that when we disable the stream install, we see that the speed here, which increases a little bit with increased SOA length. And but for the uncompressed gauge, the speed is more stable. Didn't change much. And when we enable the stream install, we didn't really see much speed improvement, though. And we saw that the bandwidth actually maybe went down a little bit. And we didn't see much performance change with the uncompressed gauge storage. And we try another lattice size, slightly different, and we got the similar results. Okay. And so here's the slash performance with the stagger phase. So that only it can potentially only affect the slash performance with the compressed gauge storage, because in that case, we need to calculate the stagger phase for the third row of the gauge field as well. And so that's typically the number we saw. So very much, not much difference here. And then we add in the naive term in our D/ code, and we didn't then we didn't see much performance difference from that as well. So typically we observed around 180 to 190 gigaflops, and the bandwidth around 130 to 140 gigabytes per second. So it may go down a little bit, but and for uncompressed gauges, the performance doesn't really change much. And so also we tested the performance of calculating the long links, which is a production of the gauge links in the naive term. And we observed typically around 300 gigaflops for the compressed gauge, and bandwidth around 150 gigabytes per second. And for uncompressed gauge, it's go down to around 180 gigaflops. And the bandwidth also went down a little bit to 134 gigabytes per second. And so here is some detailed data for that. And so we saw that with the naive term added in, with the SOA length equal 4, the performance seems to be lower than 8 or 16. And with 8 or 16, we don't see much difference in the performance here. And so here's another example, which is similar. And so conclusion. So when we test our staggered quantity gradient routine, like with the MPI and OpenMP, the code doesn't seem to be fully optimized. It has the performance of up to 45 gigaflops for the single mass inverter, and seem to decrease with multiple mass inverter and a few iterations. And also, we observed that the communication between coprocessors really limited the code performance. And for the vectorized staggered D/slash performance, with the SOA data layout, we observed the performance around 180 to 194 gigaflops for the both the naive and the D/slash with the naive terms. And for uncompressed gauge, the performance is around 140 gigaflops, and the bandwidth is around 140 to 160 gigabytes per second. And so the data layout is crucial to improve the code performance in the vectorized D/slash code. And in our case, we didn't see much performance difference from the streaming store change of SOA length or the night term. So what we're trying to do now is that we are including the vectorized D/slash code in the milk code, staggered conjugate gradient routine. So hope to get some performance analysis results for the conjugate gradient routine, which is in progress. And then also the routines for loading the links. And we are trying to get some help from Intel for the MPI proxy for code running on multiple MPI, multiple mic cards to improve the communications between the coprocessors. And we can also try the new version of Intel MPI library, which has been recently released, I think. And then the benchmarks for the vectorized milk conjugate gradients. So, so the future, I think, so there's a project that I think will be initialized in 1 year or two, called the NERSC 8, which aims to have a 10 times increase in the sustained performance than the current NERSC 6 Hopper system. And it wants to use the more energy efficient many-core architectures from the next generation of the Intel mic architecture, which is the ninth landing. So compared to the current Intel mic architecture, this one is a standalone CPU, so it can be used as a processor alone. You don't have to be connected to a processor, Intel processor, and so and also it includes the near and the far memory, and for the near memory it uses the high bandwidth in package memory, so the bandwidth might go up to 500 gigabytes per second, and it will have 2 vector processing units for each core compared to only 1 in current version. So hope that from these hardware improvements we'll observe performance that is better than our current results. And show you. So this is the one of the image that I grabbed on the website. It's not from the Intel website, but give you an idea of what this card might look like. So it will have like the near memory over here, and then the far memory will be connected with the DDR4, I think. So it's DDR4 based memory, and so they try to include like more memories nearer to the CPUs to improve the communication, and to improve the bandwidth as well. So that's all.
Okay, any questions? So I have, oh.
I have two quick questions. So first question is, what is new in Intel MPI version 5?
I'm sorry, what?
You mentioned that you want to investigate the new Intel MPI 5 version 5. What's new in there?
Okay, I searched on their website. I think they're using like a non-blocking scheme, non-blocking communicating schemes, and like one-side operations. So okay, so I think that so the non-blocking okay, I'm not sure it's called non-blocking scheme. So that means that okay, I think that means that you can take some time of like sending the message and waiting for the message to be updated to the buffer. Okay. I found some information from their website this afternoon, and probably I think I can show you the website, and then that I don't know more about the details.
I think I can look it up. Second question is this a standalone code or is it part of the Milk software library?
The vectorized stagger code is from VIII. He has he worked with some Intel staffs, and they have the Wilson D/ code, and so it's not Milk code. So we just modify that for the stagger code, and yeah.
So I assume it's not publicly available yet, like Berlin's code.
Maybe, yeah.
Okay, thank you.
But yeah.
Okay, any other questions? I have one, if there are no other. Okay, do you know why the streaming store didn't give any improvement? Do you have any thoughts on that? I mean, did you expect that it should give some improvement?
Well, we thought, we hope, yeah, we hope so. I mean, I don't know. I mean, we compared our results with the Wilson D/ code, which they do have some improvements. I mean, so I guess the differences are that we only have one spin node instead of 4, and then we have like less data to be stored, and in our case, but I'm not sure if that will actually, I mean, that was actually, I mean, show some less improvement because of that.
Mm-hmm.
Yeah. But But the thing is that we don't really see any obvious improvements right now. And I don't know if that is.
Okay, good. Any other questions? Okay, let's thank our speaker again. And we'll move to our last speaker of the day.
So it's been working here like mid-chest kind of thing. How's that? Check, check. It's okay? Okay. Got to keep your Microsoft Office up to date.
All right, let's try it.
Okay. Okay, that looks good. Are my, how about the later slides? They look empty. Okay, we're all good. Great. Okay, so laser and forward back. Good. Okay, hi. So my name's Andy Gasparo. I'm George Fleming's grad student here, and I'm going to talk a little more about spherical lattices, which Rich talked about in the first talk of the day. So we'll take it full circle in more ways than one, and talk a little bit more about radial quantization and some different discretizations of the sphere. Here's a sphere made of Legos, which they did a really good job, actually. They captured the symmetry perfectly with the color divisions. So I got that off Google. Okay. Yeah, so I'll quickly go over the motivation one more time, but I think Rich probably did a better job with it and a more detailed job of just why we want to do field theories on spheres in the first place. And then I'll give you a little background on the Reggie calculus and the kind of just the minimum amount of gravity theory that you need to sort of know about to do this. And then I'll go through the construction of the different sphere-like lattices. There are basically two that I'm going to compare and contrast. One is based on cubes, and one is based on icosahedra. And then I'll show you some convergence plots at the end. Right, so once again, we're trying to do radial lattice quantization to study conformal field theories. So for these field theories, you can map them from basically a rectangular space to a polar space by doing this map. T goes to log r, or basically r, it's an exponential map, right? R is e to the t. And then the radial part of it is, I think, not so hard compared to solving the part that's on the spherical shell. So the spatial components are the really difficult part. So the problem comes down to, can you do a quantum field theory on a sphere? So I said all that. And so our task here is to think about what's the best way to break up the sphere, and how do you take curvature into account. It's a curved manifold. So the goal for this talk is to examine those two things, basically, and try to compare and contrast the convergence of different graphs or meshes. I use those two words interchangeably. They're probably not the same thing, but they're, so if there are any mathematicians, maybe those are the wrong words, but that's what I call them. Okay, so so if most of you probably just do quantum field theories on toruses all the time, because why would you use anything else? And on those, this is lattice theory 101, naive discretization. So it's kind of basic, but it's not basic maybe if you are on a curved manifold, because you basically, you have in your action something like a sum over mu. So if you have like del squared, you have a sum over mu. So it's a sum over the number of independent directions, of course. And you want to go to something like a sum over nearest neighbors. Well, if you're on a 2 torus, then that's easy because you always have the same neighbor structure at each vertex. But if you're on, for example, a rectangular 2 sphere, then you have some vertices with 3 neighbors, some vertices with 4, some vertices with 5. And so, you know, how do you write your action? How do you change the sum over mu to a sum over neighbors? And you have to think about it a little bit. So this general approach to doing this kind of thing is called Reggie calculus. It's also called simplicial gravity. Simplicial because everything's based on triangles, tetrahedra, you know, 3-sided things. At least that's the way it's formulated for Reggie calculus. And so when you do this, you basically take a field theory which is defined in terms of coordinates, and you replace all the coordinates with labels and these invariant lengths, Lij. So there are no coordinates, everything's coordinate free. And all the information is contained in the connectivity of the graph, so the nearest neighbors, and these invariant lengths, so how far away is my neighbor. And so for when we do these constructions, we usually do it with reference to some embedding space, so spheres sitting in two spheres sitting in 3D. But once you construct the thing, it exists outside the framework of an embedding space. And for a given graph, it can look different. There's no unique way for it to look in the embedding space. So it can be a round basketball that's full of air, or it can be like partially deflated and caved in, for example. And those could be, they could give the exact same results. Right, so this is the kind of thing we're trying to discretize. And you have your square root of g here, which is basically, well, it's called a measure, but it tells you how much area, sort of, in a coordinate sense, there is at a given point, right? So that's what the curvature is, and so on and so forth. So we want to find a discrete version of this, and Rich wrote this on the board, but I'll write it one more time. So basically, you have triangles, and at each triangle, you make a little non-orthogonal basis. And at each triangle, you write your metric tensor with respect to that basis, but it's not an orthogonal basis, so it has these off-diagonal elements. And you can rewrite the entire thing in terms of invariant lengths, obviously, because 3 sides determine a triangle, and that's all the information you need. So once you do that, you have your metric, you have determinant of your metric, and now this ambiguity about how do I change my sum over mu to a sum over neighbors is removed because, well, these are your 2 directions. So you just sum over those 2 directions, and then you sum over triangles. Okay. And this is the action you arrive at, and it looks really nice. Sum over nearest neighbors, you have a squared difference, you have your invariant lengths, and then you have these area elements, which are called Voronoi dual areas. It's basically this sort of, this geometric construction. It's this thing that's tinted green here. So it's kind of just each link carries a different weight in the action depending on the underlying geometry. So yeah, and there's a little bit of the way I'm using this phrase here, Voronoi dual area. So the Voronoi cells are actually defined at each vertex, not at each link. So there's a dual area associated with a vertex, and then there's this thing is actually just chunks of the vertex dual areas. So see, these 3 lines here are the edges of a Voronoi dual cell, and so for a link, you kind of just get these chunks of these 2 dual cells. So I refer to this area and the area associated with a link by the same phrase, but I'll try and make clear which one I mean. Okay. And then I believe Rich also covered this, but there's an important note that if you write a linearized finite element method for a triangle and you do the integral, you arrive at this exact same action here, which is pretty remarkable, actually. It's so the Reggie calculus and a finite element method on a triangle are doing the exact same thing. I think that's all I want to say about that. Okay, so that's all the background. I didn't want to go into too much detail. I think that hopefully that's enough that it's a, the general understanding is there. Okay, so now we're going to move on to talking about the different kinds of lattices. So the first one I'm going to cover is what we call the refined cube, and I'll just go over how it's constructed. And there are a lot of nice pictures, so you guys, it's the last talk of the day, so you can just look at the pretty pictures and sit back and enjoy that. And then I'll talk about sort of pros, cons, why this may or may not be a good mesh, and finally, the construction of the actual field operator, which is what we care about. And then I'll do the same thing for the refined icosahedron, which is the mesh that Rich talked about. Okay, so for I have a picture which I'll flip back and forth to. Oops. So for the refined cube, it's constructed in the embedding space, and essentially you just start off with a big cube in 3D, and you break it into, well, I say S+2 blocks. The reason I say that is because the edges get cut off, and I want the final length of the thing to be S, so it's just whatever, the edges get cut off. Right, so you draw this cube in 3D, it's just a big 3D grid, and then you draw an inscribed sphere inside the cube, and you throw out the points that are outside the spherical volume. So this is kind of hard to see here, but the blue points here are all outside the sphere, the red points are completely inside the sphere, and the green points are right on the edge, and the green points are the ones you keep, and you make sure you know who is whose neighbor, and that gives you your mesh, basically. Yeah, there's some details here. You have to do it cube-wise because you can't throw out part of a cube. You want to make sure, yeah.
I mean, just a question concerning what Rich already told us this morning.
Yes.
Why not inscribe a cube and blow it up and basically find it? I mean, you're not limited. I mean, in finite element methods, you're not completely limited to triangles, right?
No.
So, I mean, is this? I don't know. Did you think about it at all?
Yeah.
Sure, but no.
Motivations here, and it's not clear. Oh, sorry. There are two different motivations here. If you write, the equation that you just wrote down, I think you have to derive from finite elements. You don't know how to write down the Laplace, the equation approximation for this kinetic term unless you have some interpolating field. If you just write that down. But Reggie calculus does a different thing. Reggie calculus writes down the gravity term, defines curvature. From curvature gets the metric tensor, and then from that metric tensor puts it into the equation for so in other words, the derivation comes from a totally different direction.
Well, okay, that's fine.
Well, so no, it doesn't. But
I'll talk about that a little bit later. Yeah, so Reggie.
My point was just, is it also another idea of using a cube to generate the lattice on the sphere, is write a cube and blow it up.
Yeah,
And end up with kind of distorted squares instead of triangles.
By the
we could do that.
Yeah.
And we could use one of those serendipitous elements.
Yeah. By the way, yeah, by the way,
no, you're right. I'll talk about it more. Sure.
It's not as different as you think. One thing that's curious, if you triangulate the cube, if you take a square and you draw a line down it, and then you use triangular elements, it turns out it has no connection along the diagonal. So in other words, if you take square patches, then you just draw lines in them.
Well, I don't want to do that.
No, that doesn't matter. In your brain, you draw them in your brain, and then you get the same elements. So they're really not independent.
The same elements.
As if you did like
a square will have, you take a hypercubic lattice, right? And then draw diagonals down them and turn it into triangles. Take finite element, and you'll get exactly the standard discretization on squares. I mean, it turns out it's an accident, if you like, it's an accident, okay? So in some sense, it's implicitly this is triangle.
Right. So yeah, I'll come back to this. There's actually you're asking exactly the right questions.
I just would, well, maybe I'll have one thing. The reason why I asked Andy to look at this cube is because I want to look at two kinds of discretization. One where all the lengths are equal and all the curvatures in the connectivity of the graph, and one where the lengths are not equal. You're probably going to say that.
Yep. Yeah. Okay. Right. Good. So this is good. These are the right questions. Okay. So yeah. So what I was just saying at the end here was the point is you keep complete cubes. So the thing that you end up with at the end, the link lengths are all the same, and it's kind of boxy, and that's what we're going for on purpose. And of course, there are other options like stereographic projections and whatnot. And I already showed you this. This is how we get the vertices. And then here are just some examples of cubic meshes with various refinements. S equals 1, it's a cube. S equals 3, and so on. And at S equals 31, you can obviously still see it only has the cubic symmetry there, but it's starting to look pretty round, so there we go. Okay, so the pro-cons. Pros, all the side lengths are equal, all the faces are exactly the same, and they're squares. And if the faces are exactly the same, then the Voronoi dual areas for each edge are the same. And this is actually, you have to be a little careful because well, if you want to think of it from the regicalculus point of view, this formula back here, I should just write it on the board because I'll refer to it about 8 times. This formula was derived using triangles, and now we have squares. So even though all the faces are the same, you can either have, so you have to draw a diagonal to make things triangles, and you can either have, for a given link, you can either have things like this, or you can have things like this. But you can actually show, so the relevant things are here and here. But you can actually show that those two Voronoi areas associated with those edges are the same, and it's kind of obvious because you just flip one of them. Okay, so like if you do a mirror flip of the right side, so that's so that's a positive. So the Reggie calculus reduces greatly. You don't have this site-dependent or link-dependent area term in your sum anymore. And another plus with the faces and edges being so regular is that the curvature at each vertex is determined entirely by the number of neighbors. So if you have 3 neighbors at a vertex, you have to be a corner either pointing in or pointing out, like this corner, for example, or that corner. And those, it turns out, are equivalent in terms of, so this is that issue of it can look different in the embedding space. You have this freedom to pop corners in and out, and it doesn't change the theory at all. And then if you have 4 neighbors, you're at a flat spot. And if you have 5 neighbors, you're somewhere crazy like here. But okay, or maybe that's, yeah, okay. Yeah, it's fine. Okay, so, and another, I think one of the first reasons we thought about looking at this was because we were thinking about in the future, we're eventually going to try to move towards spinor fields and vector fields. And if you have a nice picture of this thing in the embedding space, and if each link is associated with one of the 3 cardinal directions in the embedding space, then you have a global coordinate system, and you have an easy basis for your gamma matrices, and you might not have to worry as much about spin connections and varabines and things like that. Okay, maybe it would be even worse. Okay, so move that to the cons. Okay, so okay. I don't know. Yeah, I don't know if you want to expand upon that, but okay. All right, and so cons are the vertices don't all lie on the sphere. So this is kind of the choice you make. Either the edge lengths are all the same or the vertices all lie on the sphere. You usually don't get both. We'll look at the convergence soon, and it seems to converge more slowly to the continuum spectrum for the Laplacian operator when you put it on here. And this is just a quick note. I think I basically already mentioned this, that since all these aij's are the same, the thing reduces to a sum over this basic naive discretization. So it's the same thing as the naively discretized action for this case. Okay. But to call these things pros, it doesn't matter so much because it's not that hard to compute all these aij's. We do it for the icosahedron, so it's more of just a sort of fact. And if the spinor and vector fields aren't a lot easier, then maybe these square lattices aren't the best idea anyways. But that's an open question, I guess. Okay, so refined icosahedron, this is the mesh that Rich talked about or used in his talk. And usually the way we think, so I'm just going to go through how they're constructed real quick. Usually the way we think about it is you can sort of take this thing and flatten it out. And this is just is a diffeomorphism. It's just for visualization, basically. Because obviously, so these things are equilateral triangles. These things are isosceles. If these were equilateral, then it wouldn't be flat. But you can kind of imagine folding this thing back up and getting the same shape. And for each of these triangles on here, if we want to refine the icosahedron, we take each of these triangles and we say for a refinement of s equals 3, we divide into 3 chunks, first vertically and horizontally, and then we draw these lines across. And if the triangles are equilateral, it looks like this sort of shape right here. And this, of course, is just making just an icosahedron with more points on it. We haven't made it spherical yet. And the way you make it spherical is once you've broken up each triangle like that, you stereographically project onto the surface of the circumscribing sphere, and you get things like this and things like this. And this is what we call the refined icosahedral mesh. Pros of this, it already has the largest possible discrete rotation group. It's the best Platonic solid you can work with. The triangular faces are already a simplicial mesh, so it's simplicial mesh. So it's obvious, well, not quite obvious, but it's sort of built for applying Reggie calculus. It already has the right form. And some of the cons are the edge lengths are not equal, the shapes of the faces vary, and it's not even so much a con now that I think of it, because you have this freedom of maybe optimizing different things. For example, it might be beneficial to optimize, make the areas of each face as equal as possible, for example, or to make the points as far as possible apart. So you have options to fiddle with it a little bit, and you have to compute the Voronoi areas at each edge. So the action is this full formula here. Okay. So that's it for how you construct the meshes. So now I want to just talk about the convergence of the Laplacian. We're looking at scalar fields, so this is just the Laplacian operator stuck onto these meshes here in the way that we just talked about. So this is of course what the spectrum is converging to is a YLM spectrum. So this is a picture, I believe, of the refined cube, and you can see it starts with this purple one, and the levels look okay for the first, second, third levels, and then maybe when you get into the fourth and fifth levels, it starts to look pretty terrible. And then for higher refinements, it seems to be improving. Although, if you look very closely, even these lower levels are still split, so there might still be some problem going on. It doesn't look quite as nice as the finite element icosahedral spectrum. Okay, so the way that I decided to look at these convergences was just take each level. So there are 2L plus 1 eigenvalues at each level. Take the mean of those 2L plus 1 eigenvalues and say that it should equal some, the theoretical mean, L times L plus 1, plus some correction that vanishes like 1 over S squared, where S is the inverse lattice spacing. And then there's also some coefficient here that depends on which level you're talking about. And then there's also the standard error in the mean, which should vanish like 1 over s squared. At least that's what's expected. So we take the log and we fit a power law type thing, or fit a line to it, the log. Okay, so this is for the refined cube at the L equals 3 level, and you know, it looks okay. It's definitely, the means are certainly falling off like 1 over s squared. N is this exponent here, which is just a fit. So the means are certainly falling off like 1 over s squared, but the errors in the means don't really seem to be shrinking fast enough. They're shrinking, but maybe something like 1 over square root of s, which is not quite as good as you'd like to see. And then for the L equals 4 level, kind of a similar thing. Still the means falling off like 1 over s squared, but the standard error is falling off now even slower. But still something like 1 over square root of s. But it's not really very convincing looking, at least not to me. And probably not to you either. Okay, so what's going on? Why aren't they falling off like 1 over s squared? So basically because we weren't quite doing it right. And the reason is that the refined cube makes itself look easier than it really is. Even though the Voronoi areas at each edge are nice and easy, so the action is nice and simple, there are still non-trivial Voronoi areas at each vertex, because you can still have a vertex with 3, 4, or 5 neighbors, and each of those different situations have a different Voronoi area at the site, and that means that square root of g is not a constant, which means that you have to solve a generalized eigenvalue problem. This is just another way of saying that you want your eigenvectors to be approaching something, you want them to approach the YLM, so you want them to be orthogonal with respect to, you know, d omega. You don't want them to just be straight up orthogonal. That wouldn't exactly make sense. So, essentially this is, I realized this like yesterday, and I haven't fixed it yet for the refined cube. So unfortunately I can't show you really, really nice spectra for the refined cube right now. But I think, at least I hope, that when the Voronoi areas at the sites are included properly and the generalized eigenvalue problem is solved, it should look just as nice as the finite element icosahedron. And this is how nice the finite element icosahedron looks. It looks really nice. So here are the means converging like 1 over s squared. Here are the errors in the means converging like basically 1 over s squared. L equals 3 level, L equals 4 level. It's starting to get a little worse, but still pretty good. L equals 5 level, L equals 6 level, and that's basically as far as I looked. But I wanted to make one quick note about how I think the refined cube is going to be fixed. And this goes back to your question about why can't you do finite element for squares, for example. I think that's what should be done, is it should be something, you do finite element, you know, like this. And so on, and there are 4 of them. And I think that if that was done, it would give you the proper weights. But there's still some fiddling to be done with the refined cube, but I think that it should work out nicely. Okay, end of talk. Any questions?
I have to go and check this out by doing calculation, but you apply the Reggie calculus, and your metric tensor for a given vertex, if we write it all in triangulation, is not going to depend. So it's just the coordination number that will give you the square root of g. You have to write down the formula, but you wrote it down, right?
Yeah.
You have to calculate. There's an individual contribution from each triangle at a vertex.
Yeah.
But then you have to add them up to get the local g.
Yes.
And so you do have curvature at that g, right? So that should
Yes.
give you some g's, right? Is that what you're trying to do?
Yes,
Those are
basically.
It's just going to be numbers, 1, 2. It's just going to be, 0, 1, and 2, basically. Whatever your.
Right. So yeah. So I think another way, if you want to do it,
it's all delta function curvatures. So that will give you a weight.
Yeah. So I think that there's a non-triviality there, which comes from the fact that even if you just take a regular cube and you unfold it.
No, it's you just write.
So you still have to draw these diagonals, right?
It doesn't have any effect.
Well, it does because you have to sum over the triangles, and for certain sites, they'll have a different number of triangles around them. And it's different from just the number of squares that are around them. Even 2 corners, for example.
Okay, I have to write it down. I think not, but we'll see. But the other thing I worry about, and this is really a question for James, I'm not sure, the triangles, as I say, this is equivalent to linear elements on triangles, right? And these triangles are right triangles, which are not very good. You want to have triangles that avoid angles. As soon as you go beyond the right triangle, the Voronoi vertex, what do you call it, the circumcenter, leaves the triangle. So these are bad. So my guess is that these are just outside the realm of proper convergence for a tessellated lattice, right?
I think I even sent you.
Yeah, it's just on the boundary. So this is really just not a good tessellation, and you're going to get worse convergence. I think that's the answer.
What do you think would happen for the...
I'm asking James, but don't you think so? But I think this is, shape regular condition. I think this is right on the boundary of what's not acceptable. As soon as you get a right triangle, see if you look at the, take a look at the dual cell.
Yeah.
Right, and you'll notice that the dual cell, in fact, look at the point. You got right angles, right?
Right.
I have to go up and draw it on the board. You'll find you're just at the point that you're breaking down.
Okay.
So I think it's just
All right.
Okay, you could be right.
I just want to say that we could do this with equilateral triangles too, right? So we did this by starting with cubic tessellation of of the embedding space. We could do a tessellation of the embedding space with tetrahedra and octahedra, the surface of which would give us all equilateral triangles. So again, we would get to a graph. I mean, the point of this is to construct a graph that has all equal lengths, guaranteed all equal lengths, and then you have equilateral triangles, which is as close you get to shape regular.
This is the other standard Reggie calculus, is actually to posit equilateral triangles, right? Okay. Then all of the curvature effects comes from the vertices.
Okay, yeah.
Then you have to do an ensemble of such triangles in order to get mean curvature to be constant. No single set of equilateral triangles will either give you a good spectrum.
Right.
You'll have to then sum over it.
Right.
And I think that's also not desirable.
So I don't know. That's
a standard calculus for fluctuating geometry.
Okay.
Is to use equilateral triangles. But then you get curvature.
You don't want, the point is you don't get local curvature, continuous, you have to average over a patch to get a continuous.
Does in fact give you constant mean curvature by Reggie without changing the geometry.
Clearly, there are two different approaches, right? One is with finite elements and allowing the lengths to vary. Now you can have a curvature that varies smoothly over the graph, but you
want to get constant. You just have delta functions, that's 0, 1,
yeah.
minus 1.
Yeah.
In order to get that to be constant mean, you must take an ensemble. There's no other way.
That's not true. You average over a patch, and you can get constant average curvature averaged over a patch. The required area of the patch goes to 0 faster. Go fast enough so that it becomes continuous as you take s to infinity. Right? The area of the patch goes like a squared. So,
There's been a lot of work on optimal design triangulation. So people know, based on the surface, how to construct the optimal triangulation. I don't know, but there's a lot of people who have worked on this. And, so
as you missed, okay, let me just say, since you missed Rich's talk this morning, I mean, one of the problems that we're dealing with is the fact that we can't have exactly constant curvature across the discrete lattice, and that causes troubles for us, and we think might cause us trouble in the quantum theory. All right, you can say it out.
No, it's not the problem. Right. It's not the problem. We're getting exactly the right classical equations, right? And we are getting exactly constant curvature in the right spectrum. So that's what curvature is. It's a classical notion, nothing to do with quantum. So I actually don't think this is the problem. I think we actually have the solution to getting the right manifold. Our problems are at the level of quantum physics.
If you want to say it.
Following you.
Yeah, but
Standard finite element. It's also standard that the calculus in the case of finiteness, that's not the calculus.
What do you think would be the result of doing this thing of doing a finite element over a square and having 4?
well, there are finite elements for squares. There are lots of.
The problem with linear elements squares is that geometry is a lot more restrictive than a triangle.
Right.
So on a complex geometry, triangles are the way to go.
Right.
So it just depends on your effort. But for a sphere, I could imagine that both should work.
Well, what?
Think about the squares.
Or something.
The squares, you must keep track of lengths and angles. Data. The nice thing about simplexes, the only data is length.
Yep.
Right? So it's more complicated. That's more data. That's really in fact,
one of the things that Reggie calculus does is you can actually show that essentially it has a discrete version of the diffeomorphism invariance of changing coordinates. And it's it's a really nice way to represent a manifold.
Right.
I mean, probably there's other ways, but I think it's a really elegant way of representing a manifold. And I think, you know.
You could also use things like spherical harmonics or different bases, hanging on finite elements.
You mean on patches? Yeah, I tried that, actually. You should discuss it. No, I don't think I pulled it off right, but I tried it. It didn't seem, well, in fact, actually, this is a question for you later. But what I did try is I tried to invent spherical elements.
That's what we were.
Yeah, but I decided that there was a problem I didn't know how to solve, which was too hard an integral.
Okay. Any more questions about the talk? Okay. Cool.
Good. Thanks.
I think it's very interesting to follow. Yeah, I mean, I like your idea of asking this question because it might not be true. If you try to find the local square root of g, which is basically going to be the local curvature contribution, to see whether this does fall like 1 over s squared.
Right. Yeah, I certainly plan to.
Yeah, you should try that. I mean, I'm wondering whether it's violating this theorem of regularity or not. And it's right on the border. So it's right on the border. So probably nobody knows the answer to that.
Well, we can also do with triangular elements we want. The only one reason for wanting to do this is when you go to much higher dimensions, you eventually lose the icosahedral group, right? The icosahedron in higher dimensions, you got one higher dimension, you get the 600 cell, and then that's it. It's cubes from then on. So it's just a consequence of the way geometry works. If we want to do let's say people like to calculate the A theorem in 4 dimensions for a CFT. You're going to have to do that on an S4. To calculate the A of the A theorem has to be calculated on a sphere. And so if you want to calculate quantum field theory on an S4, the best you're going to get is the cubic symmetry.
So one thing that Andrew just said online, that there is a group that uses this, yeah, they actually have a workshop each year on finite elements. I'll email you, you might want to go. I'll have to check. I'll send you the link. We have every year. Maybe even every 6 months. Mike's the main guy working.
Okay.
Right.
Nothing if not bizarre.
It's very immature.
No, well, it's not immature. It's amazing. It comes from so many different fields, right? It comes from engineering and various practices. So the terminology is a huge, yeah. No, it's. I don't think it's immature. I think it's a vast field. Yeah, there doesn't seem to be a lot of emphasis on, I think, what's needed here, and that is the spectral problem. It's generally on the convergence of the solution with boundary conditions. See, this has no boundary conditions, so the only thing really is the spectral problem. Yeah. No, yeah. No, even the linear problem. Also, I don't see a lot on nonlinear equations. I mean, they're sort of. But you agree that there's no reason why it shouldn't work for the nonlinear equation, right? No, I mean, this is a nonlinear equation, right? This Lagrangian has a 5/4 term. There's no fundamental reason why it shouldn't converge to the classical solutions of the nonlinear equations. See, because I mean, see, the fundamental physics here is kink states, right? So you have to be able to represent these solitonic states accurately as well, right? But I don't see any reason why it shouldn't converge for those as well. That's not the spectral problem because it's not, it's not the linear problem. The Gaussian part, I'm sure we're nailing. I'm pretty sure that the nonlinear part is being nailed as well, but I'm not as confident. Anyway, it's interesting. Yeah, please tell me, can you find articles on
Okay. All right, so I think we're done. No more remote viewers. Okay, so tomorrow, the usual breakfast at 8, a different breakfast. We'll have bagels, and talks at 9, and then my plan is we'll end the workshop before lunch, and then if we all want to go out to lunch, there's a very nice dim sum restaurant within walking distance. And so I'll take a show of hands, and I don't know if we can get a reservation. I'll try and get a reservation there. But if you're interested in dim sum, we can all go for dim sum afterwards. Okay, so dinner, for those who are interested, dinner at Dolly 2 at 6:30.